Good evening, guys. Welcome back. Good evening, everyone. So, welcome back to the session, and we'll continue our discussion on fluid mechanics. Okay? मुझे पता है कि कल रात काफी लेट गया था सेशन, but it's okay. You got the day gap. Yeah. Good evening, all of you. Good evening. मैं बढ़िया हूँ. तो इतनी मेहनत से FM पढ़ते हैं, but sorry, let me read slowly. So इतनी मेहनत से FM पढ़ते हैं, बट ME में वो 2 मार्क्स के पोलर कोऑर्डिनेट पे क्वेश्चन देके बोलता है वो पढ़ के आओ. नो इश्यूज, सी विल सॉल्व पोलर कोऑर्डिनेट्स एज वेल. ओके सर, कल मैंने दिया था सारे एक्सप्रेशंस जब मैंने एक्सेलरेशन के बारे में पढ़ाया था और कर्ल सॉरी डाइवर्जेंस डिसकंटिन्यूटी इक्वेशन के बारे में पढ़ाया था. उस टाइम पे मैंने आई हैव गिवन यू दिस इक्वेशंस इन पोलर कोऑर्डिनेट्स. ओके सो कोई दिक्कत ही नहीं है, हम सॉल्व करेंगे. आई एम फाइन. चलिए, सो विल स्टार्ट द क्वेश्चंस. सो आज की सेशन में ऐसे प्लान किया था कि पहले जो टॉपिक्स ऑलरेडी हुआ था उसका क्वेश्चन हम सॉल्व करेंगे, एंड लास्ट में जो 3 चैप्टर्स है, मतलब पोटेंशियल फ्लोज का थोड़ा सा बेसिक्स और कंप्रेसिबल फ्लोज एंड टर्बो मशीन्स. ओके, जब वो क्वेश्चंस का टाइम आता है तब मैं पहले उस चैप्टर का रिव्यू देता हूं एंड उसके बाद हम क्वेश्चन सॉल्व करेंगे. ठीक है? ओके, क्योंकि लास्ट क्लास में हमने 10 बड़ा चैप्टर्स कवर किया था ऑलरेडी, so we can do that, no issue. Okay, so first we'll start with the questions. चलिए, let's start the session quickly. So obviously Abhyas for questions practice, and obviously you have Maha Abhyas continuing. Will this Maha Abhyas plus PYQs enough? मुझे लगता है कि काफ़ी इनफ है, क्योंकि जब हमने अभ्यास का क्वेश्चंस बनाया था उस टाइम पे जो PYQs आता है, ओके, और इस साल जो क्वेश्चंस आने की मतलब चांस है, सो उस क्वेश्चंस माइंड में रख के फ्रेम किया था ये सारे क्वेश्चंस. सो प्लीज follow these things. Okay, it would be more than enough, I think. Chalo, so tomorrow you'll be having manufacturing process 1 Maha revision again, and in today's class we'll start this abhyas. Okay, so of fluid mechanics. Basically मेरे पास like लगभग some 20 to 25 good questions है, काफ़ी अच्छे questions है. So we will definitely look at all the concepts basically when we try to solve the questions. Okay, and काफ़ी questions में आपको लगता है कि अरे मैंने इस क्वेश्चन पहले बार देखा था. Okay, and definitely you will enjoy the questions. Like आपने कल enjoy किया था रात 2 बजे तक, लेकिन आज उतना लंबा सेशन नहीं चलेगा. मान लो कि maximum 4 hours. Okay, 4.2 maximum. Okay, so वहाँ तक चलेगा. ठीक है? So we will start with this fluid mechanics, and of course इसके बाद we'll also have the PYQ sessions, and you know like the fluid mechanics we'll do on Saturday. Okay, so आज I think शिवम सर ने basic thermodynamics किया था, so we will look at fluid mechanics in Saturday's class. ठीक है? Are you taking maths sir? अभी नहीं, आपके लिए पुनीत सर ले लेगा वो सेशंस. ओके, लेकिन अगर आपको किसी डाउट है तो यू कैन डेफिनेटली आस्क मी. चलो, लेट्स सी. सो फर्स्ट क्वेश्चन. ओके, सो कल मैंने क्या किया, मैंने टाइम दिया था थोड़ा सा, बट लेकिन आज फटाफट सॉल्व करता हूं. ठीक है? क्वेश्चंस कॉन्सेप्चुअल होंगे क्या? कॉन्सेप्चुअल, मैथमेटिकल, सब होगा. चलो, let's solve this. A wire is attached to a block of metal. This is the metal that is submerged in a tank of water as shown below. Which graph most correctly describes the relationship between the force in the wire and time as the block is pulled slowly out of the water? Okay, so out of these 4 graphs, one graph will definitely perfectly represent the variation of the force in this wire. आप सबको विजिबल है कि यहाँ एक वायर है. सो यूजिंग दिस वायर, होल्डिंग दिस वायर, यू आर पुलिंग दिस ब्लॉक आउट ऑफ दिस वाटर. ओके, तो इफ यू नेग्लेक्ट this tension effects in the string and all, normally the string dimensions are very small, so if you neglect any extensions and all, then what would be the force inside this string? That's the question. चलो, मैंने 1 मिनट टाइम देता हूं, सोच के आंसर बताइए क्या होगा. ये B C D, ये नहीं है क्या? B, ये, अरे सोचो ना. B लगता है कि B, ये D, B, अरे C कोई टाइप नहीं किया था. Why are you not touching C? ओके, ठीक है. सो चलिए हम डिस्कस करेंगे. पहले एक काम कर लो. This is the initial position. ठीक है? So this is the mean position and this is the final position. Okay, now जब तक you don't apply any force, the block remains here. When you start pulling it up, यहां से यहां तक इस स्ट्रिंग में कुछ टेंशन नहीं होगा. Yes or no? Because if you see from equilibrium from equilibrium, okay, so from equilibrium, if you have this block, ठीक है, and मान लो कि you have a string, so it has some force which is F. Now this has some weight. At the same time, this block also has got some buoyancy force, Fb, okay. So this implies if you are pulling up slowly with uniform velocity, this F plus Fb should be equal to the weight, means the force is equal to W minus Fb, of course, okay. So this is the expression for the force in the string. काफी simple analysis है. So this is the force, which is, you can say, force in the string. ठीक है. Now observe something very carefully. When you try to pull this block up, okay, block को यहां से यहां तक आने के लिए थोड़ा टाइम लगेगा, and उस टाइम तक this block will be completely submerged inside the fluid, correct? If the block is completely submerged inside the fluid, मान लो कि अगर block completely submerged है, then if the block is here or here, it doesn't matter, these quantities will not change, correct? Yes or no? By the time this block reaches from here to here, nothing, no buoyancy changes, because whatever might be the position from here to here, the block is fully submerged again, correct? Yes or no? Come on, type in the chat box. When this block comes from here to here, then it doesn't change. इसका मतलब यह है कि पहले जो इनिशियल टाइम पीरियड होता है उस टाइम पे फोर्स ऑन द स्ट्रिंग और फोर्स इन द स्ट्रिंग डू नॉट चेंज, ठीक है. सो थोड़ा समय तक वी डोंट हैव एनी चेंज इन फोर्स, बट दीज टू ऑप्शंस स्टार्ट चेंजिंग द फोर्स विद सम इनिशियल टाइम, ओके. सो आंसर इज वन ऑफ दीज टू. देन ये और बी गलत ऑप्शन है. क्यों? एट टाइम t equal to 0 till the block reaches here, there is no change in the string force, okay. So A, B are eliminated, okay. Now C और D में क्या होगा? Let's see. When this block starts coming out, this buoyancy force keeps decreasing, correct? Yes or no? If buoyancy force keeps decreasing, what happens to the force in the string? I physically हमको भी पता है ना. मान लो कि you take a stone, okay, patthar, then you tie some thread, put it in the water, and if you take it out, when it fully comes out of the water, then definitely you'll feel more weight, yes or no, because buoyancy is absent. So compared to this inside sink, at this point, जब block यहाँ से बाहर आते हैं उस टाइम पे force बढ़ेगा, and then once it is fully out, then the buoyancy is 0 definitely. So this is the correct option and this is the wrong option. क्यों? जब even it's very simple, man. See, when block is completely inside the fluid, the force felt in the string is less, and when block is outside, then force felt is large. इतना तो पता है ना हमको. So you can see definitely if initially whatever is the force, the final force should be more than that, okay. So because of that, B and C options can get eliminated, and initially sometime till the block completely comes out, or at least it starts coming out, there is no change in the force. So D is the correct option. काफी conceptual question है ना buoyancy के. And to do this, you need hardly some 30-40 seconds, okay. But you understand it's a very nice question. मक्को उल्टा करके वाटर में डालने हैं तो फोर्स इंक्रीज करता है, बिकॉज वाटर हाइड्रोस्टैटिक फोर्स इज देयर, ओके. सो क्लीन बोल्ड. If I would choose wrong answer for this, I was thinking of not taking it this year. अरे नहीं, वैसा नहीं होगा. See, I'll tell you, कभी मत सोचो कि अरे ये बहुत आसानी क्वेश्चन है, ये मुझसे नहीं होगा, so it's not very good for me to give GATE exam. Okay, you all know what is the maths I do. Okay, एक दिन GATE 2018 लिखा हूं मैं, उसमें एक क्वेश्चन आया था, dy by dx plus x cube y is equal to 0. Sorry, xy cube is equal to 0. ये क्वेश्चन, ठीक है. एक इनिशियल कंडीशन दिया था, y of 0 is equal to something, वो दिया था, and x of y of 1 और y of 2 something they have asked, okay. क्योंकि फर्स्ट ऑर्डर डिफरेंशियल इक्वेशन है, so इसको पूरा सॉल्व करने के लिए एक बाउंड्री कंडीशन चाहिए मुझे, okay. या मैंने बताया था ना. so आपको कितना टाइम, आपको कैसा लगता है कि मुझे कितना टाइम लगेगा इस क्वेश्चन सॉल्व करने में? You know, I do this RTT, boundary layer, similarity solutions, all this that everything, okay. so आपको कैसे लगेगा कि मुझे कितना टाइम लगेगा इस क्वेश्चन सॉल्व करने में मैक्सिमम? सॉल्विंग दिस डिफरेंशियल इक्वेशन, बस मेरे पास एक बाउंड्री कंडीशन भी है, मैक्सिमम 30 to 40 सेकंड्स लगेगा इस क्वेश्चन में सॉल्व करने के लिए, हॉनेस्टली स्पीकिंग, करेक्ट? क्योंकि dy by dx इज इक्वल टू माइनस एक्स वाई क्यूब, ठीक है? सो 1 by y क्यूब dy इज इक्वल टू माइनस एक्स डी एक्स. बस जो कंडीशन मुझे दिया था मैं अप्लाई कर सकता हूं, एंड जहां जो मुझे चाहिए आई विल कैलकुलेट द y, दैट्स ऑल. ओके, बस होगा. उस दिन मैंने कम से कम 6 से 7 मिनट उस क्वेश्चन पे लगाया था, एंड फाइनली आई डिड नॉट आंसर द क्वेश्चन एंड केम बैक. ओके, honestly speaking, I'm telling you, to solve this question I spent 6 to 7 minutes and I finally did not solve this question. जब मैं एग्जाम दे रहा हूं उस टाइम पे मेरे दिमाग में यह है कि नॉन लीनियर इक्वेशन सिलेबस में नहीं है, सो क्यों दिया, बस इतना ही है मेरे दिमाग में. ओके, सो इट हैपेंस समटाइम्स, इट डजंट मैटर आउट ऑफ योर नॉलेज, बट कभी कभी ऐसा होता है कि बेसिक्स जो होता है वो स्ट्राइक नहीं हो पाएगा. सो डोंट गेट डिप्रेस्ड और डोंट फील बैड फॉर दैट. ओके, चलो. So this is the question, obviously. D is the correct answer. Okay. Then solve this question. It's जो मैंने कल दिया था homework के लिए. So let's see a multi-tube manometer. So there is air here and you have multi-tubes in this. इस question SK Soam's book से उठाया मैंने. It's unsolved question in SK Soam's book. So a multi-tube manometer using water and mercury is used to measure the pressure of air in a vessel as shown in the figure. Okay, for the given values of heights h1, h2, h3, h4, h6 तक value दिया था, the gauge pressure in the vessel is dash. Okay, so let's see. Let's start our job here. Okay, let's start our job here because we want the pressure at this point, and यहां तक चलेंगे हम, ठीक है? एंड यहां जो प्रेशर है वो होगा PATM local. Okay, that's what you want. Still getting air for it happens. Okay. Chalo, let's see. Many of my paid batch students knows me. Okay, the number of calculation mistakes I do is like exponentially high. Okay, so we should bring that down. Chalo, a multi-tube manometer using water and mercury is used to measure the pressure of air in a vessel as shown in the figure. Okay, so let's see. Let us start here. PA, for example. Okay, solution from manometry PA. Then we are at this point. So ये सब static condition में fluid inside everywhere. So whatever is the pressure here, same is also the pressure here. Correct? Because this air is in static condition, so definitely there is no change in cases. Okay, then from here to here there is air. Okay, so you have air and this air is of height h1. ठीक है? So and you are going in the downward direction. So जब आप downward direction में जाते हैं उस टाइम पे प्रेशर बढ़ेगा. So plus density of air into g times h1. So आप यहां तक आया. Then since this mercury is in static condition, प्रेशर यहां जो होता है यहां भी उतना ही होगा. Then from here to here you have mercury and the height of the column is h2 and you are moving in the upward direction. Okay, so minus density of mercury g into h2. Correct? So आप यहां तक आया. Then from here, since this is the same fluid again, यहां जो प्रेशर होता है यहां भी वही होगा. So from here to here this is water and what is this distance? This is h2 and this is h3. So ये होगा कि h2 minus h3. Okay, but you are again coming in the downward direction till this point. So plus density of water g into h2 minus h3. Okay, so h2 minus h3. So यहाँ तक पहुंच गए हमने, ठीक है? And this is also again static fluid. So यहाँ जो प्रेशर होता है वही प्रेशर यहाँ भी होगा. So now from this point let's go to this point. Okay, so what is this distance? This is h3, this is h4, so this is h4 minus h3 and you are moving in the upward direction. So minus density of mercury g into h4 minus h3. So this gives you h4 minus h3. Okay, then you went till this point and यहाँ जो प्रेशर होगा यहाँ भी उतना ही होगा. Then from this point let us reach till this point. Okay, then this is h4, this small gap is h5. So plus density of water g into h4 plus h5. ठीक है? So आप यहाँ तक आया था. Then the pressure is same till this point and from here if you go till this point you are moving in the upward direction. So minus rho mercury g into h5 plus H6. So यहाँ तक आया, and here the pressure is PATM again. Okay, so the pressure at this point is PATM local. Is this clear to all of you? तो बताओ जल्दी, यहाँ तक सबको क्लियर है या नहीं? Obviously सबको पता है कि like when we take the hydrostatics, then definitely if you move in this concept is not problem, only calculation. Yeah, that's why काफी क्वेश्चन ऐसा होता है कि जब कैलकुलेशन कॉन्सेप्ट बहुत आसान नहीं होता है, बट इफ यू डू रॉन्ग कैलकुलेशंस यू विल एंड अप विद रॉन्ग आंसर्स. ओके, सो लेट्स सी. देन यू वांट गेज प्रेशर, ठीक है. सो PATM को लेफ्ट साइड लाइए, PA माइनस PATM लोकल इज इक्वल टू, पहले जो डेंसिटी ऑफ द mercury का टर्म्स होता है उसको जोड़ेंगे. सो वो Hg इनटू, इफ इट गोस हियर H2 प्लस, then this becomes H4 minus H3 plus इसका भी H5 plus H6 होगा, correct, plus density of water. okay, ठीक है. so if you look at density of water terms, यहाँ होगा एक term, so H3 minus H2, यहाँ भी एक term है, so H4 plus H5, so minus H4 minus H5, ठीक है. so ये हुआ, and finally the last density of air term, so minus density of air into H1, this complete thing multiplied with acceleration due to gravity, बस. okay, and सब H1 H2 इसका वैल्यूज पता है हमको. so PA minus PATM, इस क्वेश्चन में कुछ नहीं दिया था, so we'll take the standard values, 13,600 into then H2 plus H4 plus H5 plus H6 minus H3. so let's see, 0.5 plus 0.7, 1.2, 1.2 plus 0.1, 1.3, 1.8 minus 0.3, 1.5. so this is 1.5 plus density of water into H3, 0.3 minus 0.245. okay, so 0.3 minus 0.5 minus 0.2 minus 0.2 minus 7, 0.9, 0.1 actually, so that's minus 1, minus density of air, so let's write this as 1000 into minus 1, minus, let's take the standard value 1.205 into H1. so H1 का वैल्यू कितना दिया, 0.4. okay, so 0.4 into 9.81, बस. okay, तीन स्टेप्स है. okay, then PA minus PATM local is equal to, सारी चीज ऐसे यूनिट्स में है, so इसका आंसर पास्कल्स में आएगा. एंड क्वेश्चन में कौन सा यूनिट्स में पूछा था, किलो पास्कल्स, so this is equal to some kilo pascals. ठीक है, so let's do the calculations then. if you do this calculation, 13,600 into 1.5 into 1.5 minus 1000 minus 1000 minus 1.205 into 0.5, you can neglect that, no issue. okay, anyway काफी कम आएगा. so 19,399 into 9.81, so 190,309 190,309 point और कुछ वैल्यूज है 2.7, so 3. so if you convert to kilopascals, 190.31 kilopascals, बस. yeah, 190.309. okay, डायरेक्ट प्रेशर बैलेंस, दैट्स ऑल. लेकिन यहां जो एडिशंस है, इस एडिशंस करने में काफी लोगों को दिक्कत आएगा. ओके, आई एम डेफिनेटली श्योर. बताओ कितने लोगों को कैलकुलेशन मिस्टेक हुआ था इस क्वेश्चन में? तृप्तिरंजन साहू, मानवित, प्रशांत, इवन, रॉयल, ऋषि, मानवित, चंदू, उज्जवल, मैकेनिकल, रॉकस्टर. ठीक है, आई कैन सी ओनली दीज नेम्स, लेफ्ट ऑल, रेस्ट ऑल वेंट. कितने लोगों को कैलकुलेशन मिस्टेक्स हुआ इस क्वेश्चन में? ऑनेस्टली बताइए. अरे होगा ना सर जी, 10 लिया चलेगा. नॉर्मली हियर नथिंग इज मेंशन्ड, सो 9.81. जब तक 10 नहीं देते हैं क्वेश्चन में, तब तक 9.81 ही करना पड़ेगा. ठीक है, या ब्लू को वाटर ले लिए मी, या इट हैपेंस, बट लेकिन थोड़ा आराम से कर लीजिए क्वेश्चंस. 190.31 किलो पास्कल्स. .31 किलो पास्कल्स. ठीक है, देन लेट्स गो टू द नेक्स्ट क्वेश्चन. चलिए, 1 मीटर डायमीटर सिलेंड्रिकल ब्लॉक. सो ये है सिलेंड्रिकल ब्लॉक. ये थोड़ा काफी अच्छा क्वेश्चन है. ऑफ मास m, सो सम मास m इज कनेक्टेड टू ए 2 meters वाइड रेक्टेंगुलर गेट एज शोन. यहां जो गेट है इसका विड्थ परपेंडिकुलर टू द बोर्ड है कि 2 meters. ठीक है, देन द गेट इज ओपन, द गेट इज टू ओपन व्हेन द वाटर लेवल h drops below 2.5 meters. जब तक यहाँ water का level 2.5 meters से नीचे आएगा तब definitely the gate open हो जाएगा. क्यों open हो जाएगा? Because this weight will pull act along this string and this is the tension T, and because of the tension this gate can rotate. Okay. Now the required mass of the cylindrical block. Okay, so what is the mass of this cylindrical block? Is dash kgs round off to nearest integer. Neglect friction at the hinge and the pulley. ठीक है. So let's solve this question. Solution. If you want the gate to be at equilibrium, then the moment about this point, let's call this point A, should be 0. Correct? So for the gate to be at a rotational equilibrium, sigma moments about point A, maybe anti-clock sense positive, is equal to 0. Okay. Now let's see, you don't know what is the mass of this block actually, but जब तक ये water level 2.5 meters तक आएगा तब ये gate खुलेगा. Correct? So it opens up. Now let's see, if you draw the free body diagram of this gate, ठीक है, ये होगा पॉइंट ए ऑफ कोर्स, एंड यहां जो हिंज है, सो हिंज की वजह से रिएक्शंस होगा Rx and Ry. Then if Rx and Ry are there, definitely here you have some tension. Okay, and this is 4 meters height of course, so there is tension in the cable. So tension ऐसे होगा. Okay, so this is tension T in the cable, and this height is 4 meters. This height is 4 meters. Okay. Now what should be the mass of the block? Now let's see, if this is tension, when the water level is 2.5 meters and this is a cylinder of 1 diameter, diameter is 1 units, you can see 1 meter, let's say 1 meter diameter, then if you look at this tension value, okay, and first of all to get the tension, let's see, you have some hydrostatic force which is also acting here, which is F hydrostatic. ठीक है, F hydrostatic, and when this gate is about to rotate, this contact at this roller support is lost. Okay, so there is no contact obviously, so no reaction at that point, just at the wedge of separation, at the wedge of rotation falling up. Okay, means the gate being open up. So let's see, so therefore no reaction at this point, because at the exact wedge of rotation the contact between the roller and plate के बीच में जो contact होता है उस contact निकलेगा. Now let's see, if you call this distance as A, for example, this implies this Rx Ry pass through the moment center, so no moments. F, this T will try to rotate the gate clockwise, so this is negative, so minus T into 4 tension times 4 plus this hydrostatic force has anti-clock moment, so plus Fh into A is equal to 0. बस this is the equilibrium equation. Correct? उसमें जो चीज है T, Fh, A, we don't know that as of now, calculate करेंगे, लेकिन this is going to be the static equilibrium equation. Is this okay to all of you? Come on, everyone type in the chat box. Will you all agree that that is the static equilibrium equation actually, for the rotational equilibrium actually in this case? So how T is right side? Because of this weight there is a tension T in the string, and this string is what this pull the gate to rotate. Okay, others, यहाँ जो string है इस string में tension है, so इस tension की वजह से this gate will try to rotate clockwise. Okay, that's all. Fine. So let's see, if you now see the quantities T, Fh, A, ये चीज पता चलना है हमको. Exactly at h is equal to 2.5 meters. Okay, so 2.5 meters, what happens? See, if h is 2.5 meters and this is a rectangular gate, why? Because it's 2 meters wide, which means 2 meters perpendicular to the plane. Okay, then the hydrostatic force acting on that will be something like this. If you project this plate, then the hydrostatic force that's acting, or you can see it's just a straight surface actually here, then the centroid of this 2.5 is somewhere here, 2.5 by 2, which is 1.25 meters deep, and hydrostatic force acting on this rectangular plate, this width is 2 meters. Okay, then this FH is equal to rho F, which is water here in this case, so density of water, G into area. So what is the area under submersion? 2.5 into this 2, so 2.5 into 2 into h bar. So what is h bar? The depth of centroid from free surface is going to be 1.25 meters. Okay, so this is 1.25 meters. So this answer is going to be in newtons. Okay, so then let's see, we need A. Okay, A we calculate करना पड़ेगा, and you know definitely the depth of centroid of the free surface is nothing but 2h by 3 from the top, which is h by 3 from the bottom actually. Okay, so 1/3 times 2.5 directly, because you know normally the center of pressure will be at a depth of 2 by 3 times the height, and 2 by 3 h is from the free surface, but this A is measured from this moment center. So if this is this full length is 2.5, A hoga ki 1/3 of 2.5. Okay, so this is 2/3 meters. Now what would be the tension T actually? Okay, that's the question. If you draw the free body diagram of this block, when this is 2.5 meters and this is 1 meter, जो depth of submersion होता है ये होगा 1.5 meters. Correct? So 1.5 meters is submerged depth actually. Okay, so maybe I'll write this as something like this. So this is 1.5 meters. Okay, and इसका diameter हमको पता है 1 meter is the diameter. Fine. So 1 meter is the diameter. Okay, so if 1 meter is the diameter, then T, which is the tension in the string, plus buoyancy is equal to M into G, mass of the block. Let's call this mass of the block as M. Okay, they have given capital M, so capital M times of G actually here. Okay, and what about FB? So T is equal to mg minus F buoyancy force. So T can be written as M into G minus buoyancy force. So buoyancy kitna hoga? Density of water pi by 4 d square, which is 1 square, into length inside the flow, which is inside the fluid, which is pi into 1.5. So this is tension, this is A, and this is FH, and sub values pata hai humko. We can substitute and get whatever is the capital M, the mass of the solid which is submerged inside the water. Okay, so let's see. This implies, again, if you put these things in this equation, you get 4 times of T, so 4 times of M, and G also there here. Sorry, this is the buoyancy. So M minus rho water into 1.5 pi by 4, this whole value, into G into 4. So this is, okay, 4 I have already written. So 4 into this tension is equal to FH into A. So FH is density of water G, this is 5 into 1.25. So this is FH into A, 2.5 by 3. That's all. You have one equation with one unknown, you can solve this. So G can be cancelled. G can be cancelled. So you can get mass in some kgs. लेकिन calculations थोड़ा carefully करना पड़ेगा. This is the mass of the gate actually. Explain A. Yeah. So normally if you have a rectangular surface, this is the case. Okay, and this is the centroid, which is h bar. Now h bar is equal to, and this height is how much? 2.5 meters. H bar is equal to h bar, which is, sorry, h star, the depth of centroid of the free surface for a rectangle is h bar, which is 1.25 plus Ixx, moment of inertia of this plane about the centroidal axis. Okay, so which is 2 times of 2.5 cube by 12, BD cube by 12 into area times again h bar, so which is 1.25. So if you simplify this, 2 into 2.25, this 2, this becomes 2.5 square. Okay, so 2.5 square into 1.25 by 12, 2.5 square into 1.25 by 12, this value plus 1.25 plus 1.25 0.25. So you'll see 1.90 is what you're getting, and if you simplify this 1/3 times of 2.5, again you'll get, okay, this is 1.90, and 1.90 if you subtract from this 2.5, okay, so if you subtract this from 2.5, you'll get 0.6 almost. That's what you would get even in this case, okay. So 1/3 times of 2.5. clear? नीचे से लेंगे by somehow, yeah, correct. Center of pressure is 2d/3, but that is from the top, okay. But here the moment center is from the bottom. See, if this is h or whatever you name it, it is depth d, then depth of center of pressure is 2h/3, but so the remaining half is, remaining part from the bottom is h/3, okay. Optics langu, okay. Yes. Then solve this question, that's all. So 5 into, so first let's, okay, let us get this term. So 1000 into 5 into 1000 into 5 into 1.25 into 2.5/3, so 5208. Then this 4 goes there, so divided by 4, 1302 plus this density of water into 1.5/4, and this would be 250. So plus 250 into 1.5 into pi, 1.5 into pi actually here. So 2480.18. Is it? I'm getting this value if you do each and everything clearly. Did anyone get this? 2480.18 kgs. So that should be the weight of the block to keep that. Yes? Okay. Many people have calculated only this value, but this is also there. No, you should simplify. You should add this term to the right side. Okay. So 2480.18 kgs is what you have. That should be the mass of the block to keep this gate static until the water level falls to 2.5 meters. Okay. It's a simple question. You see, hardly some 2-3 big steps. That's all. Okay. Yeah, this buoyancy force should be there. I know many people will be forgetting buoyancy and equating tension is equal to mg. No, that's not the case. Okay, because some part of the fluid, some part of the solid is inside. Around 4 hours. Okay, by 11 o'clock I think we can finish. Chalo. Let's go to next question. Consider the flow described by the velocity field V is equal to A into 1 plus BT I cap plus C Ty J cap, with A is equal to 1 meters per second, B equal to 1 second inverse, and C equal to 1 second square. Coordinates are measured in meters. The path line traced by the particle that passes through 1, 1 at time t equal to 0 is. Okay. यहाँ आपने जो सर टेंशन कैलकुलेशन नहीं समझा, देखो. Okay, we'll slightly go back because some of our friends did not understand the tension calculation. देखो, this string is attached to this box or whatever the body you have. Okay, so because of which there is tension, some part of this solid, and this is a static fluid obviously, so buoyancy will be acting vertically upwards. So if you see on this block you have weight and also you have some buoyancy FB, correct? So for the block to be in equilibrium, T plus FB should be same as this W. Okay, that's how. So T plus FB should be same as the weight of the block. So T is mg minus FB. Okay. Now I have given you some unsteady velocity profile. Okay, why I have given you unsteady velocity profile is because जब तक steady flow होता है तब तक first steady flow of, okay, let's see, given velocity field is A times 1 plus BT I cap plus C Ty J cap. Okay, कल मुझसे एक बंदा ने पूछा था कि लाइक सर हाउ डू यू नो द फ्लो इज स्टडी और अनस्टडी. ओके, जब वेलोसिटी प्रोफाइल्स में टी होता है, ओके, तब तक फ्लो अनस्टडी ही होगा. सो लाइक यू कैन सी इन दिस देयर इज टी इन्वॉल्वमेंट need not be in both, it can be in any one of that. Okay, even if you have one, then definitely velocity, one of the components of velocity is changing, so complete velocity vector changes. Okay, then we have for path line, this is u, x component of velocity, and this is v, y component of velocity. So since u is equal to dx by dt. Okay, this implies u, a times of 1 plus bt is equal to dx upon dt. I asked you, this is a first order differential equation, so solve this equation. Okay, so if you solve this equation, the particle which is having this path line is at the point 1 comma 1 at time t equal to 0. इसका मतलब यह है कि at t equal to 0 the x coordinate of the particle is 1 unit. Okay, so if you integrate this, let's go to the next page. So this implies a times 1 plus bt dt is equal to dx. And अगर इसको solve करना है तो, so normally you can solve the differential equation using a plus c, then substitute the boundary condition, all these things. लेकिन ऐसे भी कह सकते हैं कि at time t equal to 0 x is equal to 1. So at some time t you don't know what is x. Okay, so if you solve this, a times of integration of 1 is t, from the limits t to 0 you'll have t plus b by 2 t square, that's all, is equal to x minus 1. So x होगा कि 1 plus a into t plus b by 2 t square. Okay, so this is the equation for x. Okay, so the variation of x coordinate of the particle with time t. Okay, so वैसा होगा. I have told you yesterday, if you solve this equation you will get some function in terms of x by t is equal to 0, but here there is no y. If you have y anywhere you would have taken it as constant. Okay, but right now you see this x is some function of t actually. Clear? Fine. Now let's see similarly y. So similarly v is dy by dt. So let's solve this differential equation again. So v का प्रोफाइल कितना दिया, ct y. Okay, so ct y is equal to dy by dt. तो अब कैसे करें, ct dt is equal to 1 by y dy. So फिर से इंटीग्रेट करें. At time t equal to 0 this y is equal to 1. So at some time t you don't know what is this y. So let us solve this differential equation. So if you solve this, c t square by 2 is equal to ln integration of 1 by y is ln y, and when you put the limits ln y minus ln 1, so ln 1 is 0. So this is what you have. So y is equal to e power c t square upon 2. So this is the y equation. Okay, so y is given by e power c t square upon 2 actually here. So at any given time the x comma y coordinates, if you want to write the path line equation, the x comma y coordinate at any point is this comma this, and I think abc values are given. A is 1, b is 1, c is also 1. So definitely no need to put abc values. For a equal to 1, b equal to 1 and c equal to 1, this implies x is equal to 1 plus t square by 2 and y is equal to e power t square by 2. That's all. Okay, so this would be the path line equations which connects the things. So x is equal to, okay, they have given in terms of a comma b. Okay, so if you have a comma b, let's put it in a comma b. So x is equal to 1 plus a times of t plus b by 2 t square, a into t plus b by 2 t square plus 1, and here you have plus 1. So x coordinate is correct. What about the y coordinate? C power t square by 2, c t square by 2. Yeah, first option is correct. That's all. First option is correct option in this case. Okay, here the mistake is -1. Here this t doesn't have anything, and this option is also same as first option. No, this 2b is there, so this 2 is wrong. So a is the correct option. Okay, this is the way to get the path line equation. And if profiles are simple, we can eliminate t from both the equations. कल जब मैंने आपको थियरी पढ़ाया था उस टाइम पे मैंने बताया कि पहले इस इक्वेशन को सॉल्व कर लो, यू विल गेट सम फंक्शन ऑफ x by t इज इक्वल टू 0, एंड उसके बाद इस इक्वेशन को भी सॉल्व कर लो, यू विल गेट सम डिफरेंट सॉल्यूशन f2 of x by t इज इक्वल टू 0. फ्रॉम these two you can eliminate t. Okay, that's how you get the equation, but here they have directly given in terms of coordinates, so you can use this. ठीक है, सबको समझ में आया कि पाथ लाइन कैसे कैलकुलेट करना पड़ेगा. एलिमिनेशन ऑफ t, ठीक है, अगर करना चाहिए तो कर लो. t is equal to, if you put c is equal to 1, okay, so if you put c is equal to 1 in this case, for example, so this implies t is equal to square root of 2 into ln y whole power half. That's what. Okay. So t square by 2 is equal to this. So you can put t is equal to here. So x is equal to 1 plus t. So root 2 ln y power half plus half into t square. So 2 times ln y. X is equal to 1 plus ln y plus root 2 into ln y power half. That's all. So this is in terms of x comma y if they ask you. Why we took x is equal to 1? Because you see this particle to which you are drawing the path line, that is passing through 1 comma 1, means at time t equal to 0 the value of the x coordinate of the particle is 1. Okay. So सबका समझ में आया कि नहीं पाथ लाइन कैसे कैलकुलेट करना पड़ेगा? Okay. Sometimes you see people teach this in a different sense, like they write u is equal to dx by dt, v is equal to dy by dt, and obviously if you divide this then you'll get streamline equation again, dx by u is equal to dy by v. Okay, but this is valid only if the flow is steady. Okay, if there is unsteadiness in the flow then this approach fails. Okay, like if you try to apply this integration here, you won't get the answer because you'll have t in the function but you won't have integrating variable as t. Got it? I am integrating things because I have space integral and also time integral. But मान लो कि मैंने इस equation apply किया था, so dx by u equal to dy by v, there is no time derivative. Okay, but in the functions you have time. Then how will you integrate that? You cannot do. Okay, so that's why that's valid only in the cases study. ठीक है? But this is the classic way to solve for any path line equation in reality. Can we apply this in study? Yeah, why not? स्टडी में इससे ज्यादा आसान ही आएगा आंसर. ओके, चलो लेट्स सॉल्व नेक्स्ट क्वेश्चन. The viscous boundary layer velocity profile is approximated by a cubic equation given by u of y is equal to a plus b into y by delta plus c into y by delta whole cube into u infinity. The boundary conditions u equal to u infinity and at the boundary edge delta, which of the following options gives the correct values of a and bc? Assume that the viscous friction is 0 at the boundary edge and no slip condition at the outer edge of the boundary layer. Okay, so the same thing, you have this profile, you need 3 equations. You know what are the 3 equations, just get the answer. Steady flow में तो streamline path line equation same होगा ना sir? Yeah, if you have a steady flow then streamline, path line, streak line जो चीज होता है वो सब एक ही आएगा. I'm genius in maths, thank you man. Anyway, little maths. चलो let's solve this. So हमारे पास जो आएगी velocity profile, given u of y into u infinity. So let's bring it here. U by u infinity is equal to some constant a plus b times y by delta plus c times y by delta whole cube. Okay, so this is cube. ठीक है, so इसके साथ values भी है हमारे पास. So let's calculate this. Okay, so let's calculate. Anyway, कल मैंने किया था इस क्वेश्चन. So 2 times y by delta minus half into, okay, this is like 3 by 2 maybe. Let's see, we don't know as of now. So firstly, at y equal to 0, u equal to 0. So this implies a is 0 straight away. Okay, at y equal to delta, u tends to u infinity. So this implies 1 is equal to b plus c. So b plus c values is 1. इतना information तो sufficient है. a equal to 0, 0, 0. So this is wrong. a is not 0. And b plus c का value 1 होना चाहिए. ठीक है. So b plus c 0.5 wrong. b plus c 1 possible. b plus c 1 possible. लेकिन ये दोनों ऑप्शन सेम ही है. करेक्ट. प्लस 0.5. ओके, क्योंकि दोनों ऑप्शन सेम ही है एक्चुअली, we should have got eliminated. If you want the third condition, if you want to fully solve the equations, then कैसे करें? Let's see. At y equal to delta, dou u by dou y is equal to 0. ठीक है, क्यों? वेलोसिटी वहां मैक्सिमम आएगा एंड उसके बाद वेलोसिटी नहीं बढ़ेगा. सो देयर इज स्टैटिक पॉइंट वेयर वेलोसिटी डू नॉट इंक्रीज. सो उसके बाद अगर आपने y को बढ़ा तो भी वेलोसिटी नहीं बढ़ेगा. ओके, सो dou u by dou y is equal to 0. So if you integrate this, 1 by u infinity into dou u by dou y is equal to a is 0 anyhow. So b by delta plus 3c y square by delta cube. ठीक है, and if you put y equal to delta, this term is 0. So if you put y is equal to delta, you have b by delta plus 3c by delta is equal to 0. So b plus 3c should be 0. इसका मतलब है कि b should be minus 3c. So if you substitute, this is the third equation. ठीक है, so you can see if you put b equal to 3c, then 1 is equal to c is minus b by 3, c is minus b by 3, so 2b by 3, so b equal to 3 by 2 which is half. ठीक है, and इसकी वजह से c होगा minus 0.5 because b plus c should be 1. That's how you'll get 0, 1.5 and minus 0.5. This condition is, third condition is not clear. ठीक है, look. ठीक है, सो ऐसा होगा वेलोसिटी प्रोफाइल. ये सबको पता है ना. Why you have taken du by dy equal to 0? I'll tell you. Just a second. If you see, this is the velocity profile. यहाँ जो velocity होगा 0, ये पता है सबको. And if you look at velocity here, here also you reach almost 99% of the free stream velocity. This is also fine. Now, if you start looking at du by dy, okay, du by dy or dou u by dou y, whatever, if you take this term tells you when you change y by some small amount, u में कितना change आएगा, correct? That's what this term tells you. Yes or no? मान लो कि आपने y को थोड़ा सा change किया था, then what would be the change in velocity u? That's what this term tells you. Okay? Agreed, all of you? Yes? Now, once you reach this point, so here to here, here to this delta means basically in this domain, yahan tak, if you start increasing y, your velocity keeps changing. But once you reach this point delta, okay, so this is delta. So अगर आपने एक बार यहां तक आए तो after this, even if you change y, will your u increase or will your u change? Because you have already touched the free stream velocity and outside there is no viscous effect. ठीक है? So then at this point, if you change your y, will your u change? नो. तो तब इसका वैल्यू कितना होगा? तो मान लो कि आपने y बदला है लेकिन u नहीं बदलेगा. Then what would be the value of dou u by dou y? 0. बस इतना ही है ना. So then if this is changing but this is not changing, so u is not changed, so du by dy is 0. Outside boundary layer u will be constant. For flat plate it is constant. Okay? मान लो कि आपके पास एक स्पीयर है एंड स्पीयर में कुछ फ्लो होए, उस टाइम पे नहीं होगा, बट जब तक आप फ्लैट प्लेट की एनालिसिस बात करें तो तब तक u इन्फिनिटी कांस्टेंट ही होगा. ओके, अगर आपको फोर्थ कंडीशन भी चाहिए तो डो स्क्वायर u by dou y स्क्वायर एट y इज इक्वल टू 0 इज इक्वल टू 0. क्यों? dou u by dou y सबसे ज्यादा यहां मैक्सिमम होगा. Okay, like as you move, the effect of change in the velocity, the dou u by dou y decreases. Okay, so here it is maximum, and as you move up, finally you reach 0. After that there is no change. Okay, which means dou u by dou y changes maximum at this wall. So that's why dou by dou y of dou u by dou y, because at y equal to 0, dou u by dou y changes maximum. So that's why you have this is equal to 0 actually. Okay. Yeah, shear stress is maximum. You can go with that understanding also. Tau equal to mu into du by dy. So d tau by dy is equal to 0 at wall. So obviously d square u by dy square is 0 at wall. Okay. If you have the fourth condition, for example, if someone asks you, पहले ये 3 करना चाहिए, इसके बाद मान लो कि fourth condition भी चाहिए तो you can apply this. Okay. But generally they'll ask you only for 3. चलो, then see. So solve this question. A plain gate of uniform thickness, so thickness deep into the water, holds back a depth of water as shown. So ऐसा कुछ हो है. The minimum weight of the gate required to keep the gate closed is dash kilonewtons round off to 1 decimal place. Fourth condition is not necessary, it's optional. जब तक ये fourth variable है तब तक नहीं चाहिए. ठीक है. So मान लो कि मैंने दिया था कि a plus b into y by delta plus c into y by delta whole square plus d into y by delta whole cube, then you should have this. Okay. So let's see. This is the gate. Okay. And because of the weight of the gate, this gate is landing. Otherwise what happens? Because of this water pressure, this gate should rotate. Okay. Rare cases, yeah, generally if they want to put you in loop, then they can give you such questions. So chalo, this is 30. Okay, so theta is 30 and width of the gate is 2 meters and you have water. Length of the gate is 3 meters. Okay, what should the weight of the gate? So physically क्या होता है? This water will try to exert some hydrostatic force on this gate. Okay, and obviously the gate will have some weight. So because of this, they both balance and the gate will be there. So if it has to hold this much amount of water, if any slight increase in level, this will tip off. Means basically this gate starts floating. Okay, so let's see how do we solve this question actually. So this is the gate. Here you have liquid and on the other side you don't have any liquid, of course. Okay, you just have the atmosphere and here also this is free surface. So let's see solution. Oh sorry, so this is the hinge. Okay, so यहाँ एक hinge है. Then theta is 30. So here the weight of the gate would be there. Okay, weight of the gate, and definitely hydrostatic force will act somewhere below the centroid. So this is G. So let's say this is somewhere you have the center of pressure and you have normal hydrostatic force like this acting. So this is F H. Okay, and this angle, ये कितना है? So this angle is basically 30. Okay, so 30 and length of the gate is 3. Meters. Okay, so this is 3 meters. Now if you want to calculate the depth of center of pressure and also the centroid, can I make a small assumption just to get the magnitudes? Because if you have fluid on this side and air on this side, or if you swap like fluid here and air here, the only thing that changes is this direction of the force. Center of pressure वही होगा and total जो magnitude of the force होता है वो भी same आएगा. Correct? So let's say if I take for example this as 30, then the magnitude of the hydrostatic force that's acting is equal to rho F G A into H bar. Okay, and this is going to be rho F G. What is the area of the gate which is submerged? This length is 3 meters and width of the gate is 2 meters. Correct? So 3 into 2 into, so what would be H bar? H bar would be this one. Okay, so this is H bar and this total is 3. So definitely this value or this vertical height is going to be 3 sine 30, so 1.5. So this H bar is going to be 0.75. That's all. Okay, so this gives you rho F G into 6 into 0.75. Of course it's going to be integer, some decimal, 1 decimal, 4.5. Good. So this is the hydrostatic force. Now since you cannot directly get the moment about this point A, हम क्या कर सकते हैं? इसको resolve कर सकेंगे. So you have this component and also one component acting along this length. So अगर weight W होगा तो इस component कितना होगा? What would be this angle? Can someone tell me? This is the angle between the plate and the horizontal. So normal to the plate and vertical would also be theta. Correct? मान लो कि अगर ये theta हुआ तो ये भी theta होगा. So W cos theta and W sin theta. ठीक है, and W sin theta will be W cos theta will be exactly at a distance of L/2 moment arm. Okay, then what should be this value? So let's say if you need this value, which is the depth of center of pressure measured along the plate, so H star is equal to, so H star मतलब मान लो कि this is the point. Okay, so ये होगा H star, and you have H star, you have A, and this angle is 60 degrees. Okay, so if this is 60, then definitely you know tan or cos 60 is equal to H star upon A. So this is H star is equal to A by 2, or A is equal to 2 times of H star. Correct? So let us substitute this. A is equal to 2 times of H star actually here. So if you substitute H star first, H bar is 0.75 plus calculation of moment of inertia. So if you see the plane, this is the case where the length is 3 meters, width is 2 meters. Okay, so the length of the plane is 3 meters and width is 2 meters, and you have the centroid somewhere here. So Ixx about the centroidal axis is BH cube by 12. Correct? So BH cube by 12. So 2 into H cube by 12 into sin square theta. So here this angle is 30. So sin square 30 is obviously 3 by 2 again. So sin square, sorry, 30. Sin square 30 is 1 by 4 into A times H bar. So 2 into 3 is 6 into H bar, which is 0.75. So this is H star in some meters. Okay, so this is H star in some meters. So लेंथ को sin 30 में रिजॉल्व करना, लेंथ को sin 30 में रिजॉल्व नहीं करेंगे, नो, ऑब्वियसली नॉट, नो, बिकॉज सी व्हेन यू इफ यू, अगर आपको याद है तो लास्ट क्लास में भी मैंने महाविजन में भी कवर किया था, अगर आपको ऐसा है प्लेट इंक्लाइन, ठीक है, and then if this is the area, if this is the centroid, you will calculate the moment of inertia about this axis for this full figure. Okay, it's not the vertical figure. Clear? So that's what. ठीक है, जो मोमेंट ऑफ इनर्शिया आप कैलकुलेट करें वो पूरा एरिया के लिए कैलकुलेट करें, नॉट फॉर द प्रोजेक्शन. या 11,000, oh 1,13,276 kgs maybe. Anyway, let's see. It's a 3 meters gate, so 3 meters is काफी बड़ा gate है. So let's simplify this. How will we simplify? Let's use calculator directly. So 27 by 2, 13.5 divided by 12, 6 are 72, 72 into 0.75. So 0.25 plus 0.75. So H star is 1 meter. Okay, so if H star is 1, then this implies A is equal to 2 H star, which is 2 meters. Okay, so this A is going to be 2 meters. So A is equal to 2 meters. Clear? And this W cos theta will be at 1.5 meters. Now, if this gate has to be under equilibrium, the summation of moments about this point A has to be 0. Okay, so 1 meter. Okay, therefore A is equal to 2 H star, which is 2 meters. So for equilibrium, summation of moments about point A, maybe you can take anti-clock sense positive, so this is 0. Now if you see, out of the resolved components, this point A has hinge reactions Rx Ry, लेकिन वो जो hinge reactions होता है वो मोमेंट आर्म से, सॉरी मोमेंट सेंटर से पास होगा. Rx Ry W sin थीटा, ये तीनों कंपोनेंट्स डिग्री का 60 आएगा या 30. Degree is 30, but in this geometry if you see, this angle with the vertical would be 60 for the plate. Okay, you can see the angle of this plate with horizontal is 30, so vertical से 60 होगा. Okay, that's why it is 60. So h star and a, so since this is 60, cos 60, because ये जो right angle है, so ये cos 60 is equal to h star, so h star is equal to a by 2. ठीक है. Then so if you solve this, summation of moments w cos theta, where theta is 30 in that case, so w cos theta into half of the length, which is 1.5, is equal to hydrostatic force, density of the fluid g into 4.5. So this is the hydrostatic force that you calculated. So Fh, this is the hydrostatic force multiplied with this length is 2 meters. That's all. Okay, and what do you need? Weight of the gate. Okay, so W is equal to some newtons, and they're asking you in kilonewtons. Okay. Excuse me. So let's solve this. So 1000 into 9.81 into 9. So 9000 into 9.81. So this value divided by 1.5 into cos 30. So cos 30 is root 3 by 2 actually. Okay. So divided by square root of 3 into 1.5. Okay. So square root of 3 into 1.5. So this is the value into 2. So 67965. 67965 point और कुछ decimal से 7 लगभग. So if you do it to kilonewtons, 67.96 kilonewtons. Okay, so what is the value again? Round off to 1 decimal place. So you can take 68 almost. Okay, so 68 kilonewton. That's the answer. Yeah, 67.96. So 67, whatever, they'll give you some range in final exam definitely. लेकिन जो angles and when you calculate the hydrostatic forces, you should be doing it correctly. Okay, कुछ mistakes नहीं होना चाहिए यहाँ. ठीक है? Lord Voldemort, did you get this thetas actually? Everyone. तो मैंने सही किया कि मास 113276 ही आएगा. अच्छा, इज इट? लेट्स सी. डिवाइडेड बाय 9.81. मास इतना होगा ना 6928. मास 6928 केस होगा नॉर्मली इस प्लेट का. मतलब 6.8 टन्स रफली. ओके, नॉर्मली मैंने हर एक क्वेश्चन ऐसे सेट किया था कि we are handy to do these kind of questions. अगर प्लेट ऐसे इंक्लाइंड है तो, एंड इफ यू हैव फ्री सरफेस, बहुत आसान से कर सकते हैं, फॉर्मूला से सब याद होगा. ओके, बट इफ यू टिल्ट द प्लेट लाइक दिस, ओके, देन पीपल डू मिस्टेक्स, जैसे आज होगा. ओके, सो एंगल वाला एक बार एक्सप्लेन कर दो, थोड़ा कंफ्यूजन है. नॉर्मल केस है, एंगल में 60-30 में अटक गया. ऑफकोर्स, सी आई विल टेल यू दिस एंगल. व्हेन यू हैव द फोर्स हियर एंड दिस इज द थीटा, Fh magnitude and point of application do not change even if you have fluid here and air here. Okay, so I have calculated these values Fh and H star using the assumption that water is on this side and air is on this side. Okay, so that the magnitudes remain same. Clear? अगर किसी को किसी डाउट है तो बताओ, मैं एक्सप्लेन कर सकता हूँ. बिकॉज मैंने ऐसा क्वेश्चन सेट किया कि जहां काफी लोग मिस्टेक्स कर सकते हैं. सो आई वॉन्ट यू टू क्लियर ऑल योर कॉन्सेप्ट्स टुडे. कल हमने लेक्चर दिया था, लंबा लेक्चर, बट लेकिन उस लंबा लेक्चर का आज प्रैक्टिस भी होना चाहिए. डब्ल्यू कॉस थीटा वाला में करेक्ट. कैन यू प्लीज टॉक अबाउट द फोर्स कॉम्पोनेंट? ठीक है. सो इफ यू सी, if you have W like this, okay, then this see, I'll draw the diagram maybe here. तो मान लो कि ऐसा है, ठीक है, and W is like this. Then compared to this point, it's not very okay for you to calculate this distance. It's okay if you want, you can calculate, but the rotation of this gate will be not along this. It should be perpendicular to this. So we have resolved. Wagnon theorem, bus. Okay. This resolution, what we have done, is purely because of Wagnon's theorem. Okay. I have resolved W cos theta and W sin theta. अगर नहीं होना चाहिए तो see. I'll tell you one thing. काफी लोग को confusion है, कोई दिक्कत नहीं. Look. So you have weight W. ठीक है? If you have this W like this, so let's say this distance between this line of action and this is, for example, say 1, okay, A1, okay, you talk it A1. Then the moment of this load about this point is nothing but W into A1, okay, and you know this angle is 60 degrees, okay, so this angle is 60 and this length is L by 2. L by 2, ठीक है. So if you take the moment W into A1 कितना होगा? So this is A1. A1 is L by 2 sin 60. Okay, L by 2 sin 60 degrees. Then L by 2 sin 60 degrees, which gives you WL by 2 into root 3 by 2. Correct? ये आएगा. Now what I have done? I have just resolved this into two parts. That's all. ठीक है? I just resolved that into two parts. Clear? So if you resolve this into two parts, तब क्या होगा? You have the same plate. Okay? मैंने क्या किया? This is W cos theta. So cos 30 is root 3 by 2. Correct? So because if you see, this theta is same as this theta. So if this is 30, this is W cos theta. So W into root 3 by 2. This is the center and W sin theta will pass like this. Okay. Now, if you write this summation of the moments, W root 3 by 2 into, this is normal to this point. So this is L by 2 plus W sin theta. And this component is passing through this moment center, so no moment arm. So you will have W root 3 by 4 into L. This and this are same actually. Understood? And this is nothing but the Wagnon's theorem, जो mechanics में आप लोग statics में पढ़ाते हैं. So F into D is equal to summation Fx dx. Correct ना? दोनों चीज एक ही देते हैं पक्का. They should come obviously, right? Basic Wagnon's theorem ये. ऐसा PYQs भी है actually. Okay? So center of gravity 1.5 meters पे है ना? Obviously, क्योंकि plate uniform density का है ना, so obviously midpoint of the plate में होगा. Understood guys? गेट में ऐसे क्वेश्चन आते हैं. सी, क्योंकि ये क्वेश्चन इतना लंबा नहीं है, मैक्सिमम इट कैन बी सॉल्व्ड इन 2 minutes, 1 minute or 1 minute, 3 minutes maximum. Okay, maximum for 2 marks they can give you, and these kind of questions even came in GATE mechanical. अगर आपने 2016 या 15 के पेपर्स खोला तो मिलेगा. Okay, so shall I go to the next question now? Center of gravity is 1.5 meters पे है. Yeah, obviously, because center of gravity is exactly same as the geometrical center if the body is of uniform density. ठीक है? चले, सारा डाउट्स क्लियर है या नहीं? एक बंदा ने मुझसे पूछा था कि इस एंगल थीटा कैसे हुआ. नॉर्मली एक रूल है मैथ्स में, द एंगल बिटवीन टू लाइंस इज सेम एज एंगल बिटवीन देयर परपेंडिकुलर्स. तो ये भी थीटा होगा तब. ओके, क्लियर? So you see, if this angle is theta, the angle between the normals is also theta. सबको पता है कि कैसे? Like दिस इज 90, दिस इज 90, सो ये होगा कि 180 माइनस थीटा। तो अगर ये 180 माइनस थीटा होगा तो ये होगा थीटा, दैट्स ऑल। ओके, नाउ using this technique, if the angle between the plane and the horizontal is 30, then angle between normal to the plate and vertical is 30, that's all। ठीक है, one doubt, h bar and h star vertical position पे लेंगे, exactly, so always your h and h star should be measured vertically, clear, slant से नहीं measure करना पड़ेगा। all your expressions h is the vertical coordinate, ठीक है। काफी लोग यही मिस्टेक करते हैं कि h स्टार अलोंग द प्लेट कैलकुलेट कर सकते हैं, बट दैट्स रॉन्ग, क्लियर। फाइन, ठीक है, सो आगे चलेंगे यहां से। प्लीज गिव मी परमिशन टू मूव फॉरवर्ड। ओके, सो आई एम मूविंग फॉरवर्ड। किसी को कुछ डाउट्स नहीं है यहां तक? सबको जो क्वेश्चन हमने किया था वो सब क्लियर है ना? ठीक है, चलो लेट्स मूव, सॉल्व कर लो इस क्वेश्चन। ये क्वेश्चन मैं नॉर्मली कॉम्प्रिहेंसिव कोर्सेस में सॉल्व करता हूं, बहुत कॉन्सेप्चुअली क्वेश्चन है, सो लेट्स सॉल्व दिस क्वेश्चन। ये क्वेश्चन मैंने सेंजल से उठाया था, तो अनसॉल्व्ड क्वेश्चन अगेन। ए यूनिफॉर्म वुडन रॉड, सो ये जो रॉड है ये है वुडन रॉड, ठीक है। Wooden rod of diameter 4 cm, length 8 meters, is immersed in water, density 1000 kg per meter cube, and is hinged without friction at point B. So at this point you have the hinge on the water line. So this is exactly water line. Okay, a solid spherical ball having mass of 2 kgs of lead, specific gravity 11.4, is attached to the free end of the rod to keep the assembly in static equilibrium inside the water. The specific gravity of the wooden rod is dash. Okay, round off to 2 decimal places. Assume radius of the ball is much smaller than the length of the rod. ठीक है, so let's solve this question quickly. Let us start with the free body diagram. ठीक है, there is a wooden beam. Okay, onto this you have a lead ball जिसका diameter इस लेंथ से काफी छोटा है, ठीक है। Then let's see if this is the ball that we have attached. Fine, this is the hinge at this point, so obviously जब hinge होता है reactions होगा Rx and Ry are the hinge reactions, ठीक है। Then let's see, definitely इसका जो weight होता है is weight of the beam, let's see W of the or wood for example, okay, weight of the wood, weight of the ball, okay, weight of the wood and weight of the ball definitely. Now since this complete configuration is inside the fluid and exactly complete beam is submerged inside the water, okay, and this ball is also submerged inside the water, तो क्या होगा? We have the buoyancy at this point, so this is buoyancy on beam or buoyancy on wood and buoyancy on the ball actually here, okay, these are the things। GBG 8 में था इस क्वेश्चन, अच्छा ठीक है, I don't know, maybe in fluid mechanics people might have given, but this is a question from Senjal actually, okay, and Frank and White also has this question actually। चलो let's solve this। In solving this question, if you take about the hinge, then if this distance is A and if this distance is B, ठीक है, then again this complete configuration has to be in stable equilibrium, okay, so if that has to be in stable equilibrium, about this point the rotation should be, the net moments should be 0, so this point is B actually, not A, whatever। So for rotational equilibrium, sigma moments about this point B taking anti-clock sense positive, so is equal to 0. Now you'll get this angle with the horizontal is theta, so this angle is also theta, and this angle is also theta, obviously. Okay, then F buoyancy on wood into A plus F buoyancy on the ball into A minus weight of the wood, sorry, this is B actually, into A minus weight of this ball into B is equal to 0. Correct? Now, so if body is fully submerged, center of buoyancy and center of gravity will coincide. Yes. See, generally that happens only if the body is uniform, mass in the body is uniformly distributed. मान लो कि हमने कुछ क्वेश्चंस किया था कि like stability of submerged bodies. Okay, उस bodies में हम stability के लिए body को bottom heavy बनाते हैं. Correct? उस bottom heavy bodies में center of gravity नीचे आएगा, and center of gravity जो geometrical center of buoyancy जो geometrical centroid होता है वहाँ होगा. Okay, so you will have G and B coinciding in completely submerged bodies only if the body you submerged is of uniform density everywhere. ठीक है? Body should not be like heavy at the bottom or heavy at the top, वैसा नहीं होना चाहिए. Clear? Moment of the lead ball about hinge plus moment of the weight is equal to moment of hydrostatic pressure. It's all by this approach. Moment by hydrostatic pressures. Moment of lead ball about hinge, moment of weight. Obviously, that's what the hydrostatic pressure is. These two. Okay. So if you see this term buoyancy on the ball, I am neglecting it. Okay. Why? ये काफी छोटा होगा. Okay. So this would be very small, and clearly you can observe B is going to be 2 times of A. Correct in this case because similar triangles. So this is half of the length and this is full length. So A and B will also be half. Both are right angle triangles. So by simple similarity, you can see A, B are zeros. Okay. What about buoyancy force? Sorry, what about hydrostatic force? Buoyancy itself is the hydrostatic force. Okay. It is hydrostatic force on the solid. Those are surfaces. Clear? The buoyancy on a solid is nothing but the hydrostatic force actually. Okay. But it's on a body, not on a surface. In fact, I did not dive in last class in the Maha Abhyas, but if you try to calculate the buoyancy force using Archimedes principle, you will calculate using the hydrostatic force only. Okay. Chalo, let's solve this. So if A is equal to 2B, then yahan hoga 2. So which tells you density, this is buoyancy force on the wood. So density of water, so density of fluid, let's talk, pi by 4 d square into length of the wood into G. This is neglected, very small, minus weight of this wood. So density of the wood pi by 4 d square wood into length of the wood into G minus 2 times of weight of the this term, weight of the ball actually. Okay. So weight of the ball is nothing but mass of the lead ball into G actually. Okay. So they have given 2 kgs of lead, direct mass of the lead is given to you. Now you know everything, you just need to figure out what is this density of the wood, that's all. Okay. So if you divide with density of water all over, so this gives you specific gravity of the wood. Okay. Now what is the diameter of this? Diameter is 4 centimeters. Okay. So diameter is 4 centimeters. So which can give you pi by 4 0.04 square into this G can be cancelled in all the terms. Okay, because right hand side is 0. So pi by 4 d square into length of the wood. Wood length is 8 meters. So into 8. If you take this common, then 1 minus specific gravity of the wood is what we have, is equal to 2 times mass of the ball, 2 kgs by density, which is 10 cube for the water. So one equation with one unknown you can solve. That to a linear equation. Specific gravity of the wood is equal to, you'll get some value, 4 by 1000, 4 by 1000, okay, into 4 divided by 8 into 0.04 square into pi, okay. So 0.397. So subtract 1 from this, so add 1. 0.602 is the specific gravity of the wood, okay. That's what. Clear to all? Is this okay? 0.602, 0.607. Maybe if you take this, hydrostatic force will be cancelled from both sides, no? See, if you, I'll teach you this. Look carefully. Maybe you're getting this doubt because of these things. If you have a body submerged, okay, like this, and let's say some free surface is somewhere here. If you take a small area dA, let's say this is some distance z and dA here, यहाँ जो प्रेशर होता है वो होगा P, देन डेफिनेटली यहाँ प्रेशर होगा P प्लस रो एफ जी जेड, करेक्ट. सो अगर आपने इस स्मॉल एलिमेंटल एरिया का फ्री बॉडी डायग्राम बनाया तो P प्लस रो जी जेड डी ए, P times dA, okay. Then the net force in the y direction is going to be rho f g z dA, okay. And this z into dA is nothing but the elemental volume, the volume of this body which is inside the fluid. So if you want, this is dfy, okay. So this implies full fy, which is nothing but the buoyancy force, is nothing but rho fg into, for small element this is small volume, so this is the full volume which is submerged. This is how you get the buoyancy, okay. Understood? It's not because of the hydrostatic force acting at a point, like obviously everything here gets cancelled, that's why I'm not writing this, okay. But whatever is there here, perpendicular in the direction perpendicular to the lines of constant pressure, that exists, okay, and that is responsible for the buoyancy. Clear? मैंने ये सब नहीं लिखा क्योंकि वो कैंसिल हो जाएगा. जो आर्ग्यूमेंट आप कर रहे हैं प्रशांत वो सच ठीक है एक्चुअली, ओके, बट buoyancy is not because of that forces, it's the difference in the pressure along the length. Clear? Come on guys, quick. Clear? काफी लोग इस क्वेश्चन ऐसे सॉल्व करते हैं कि सिग्मा fy is equal to 0 लिखते हैं and equate these two with these two, which is wrong, okay, because in this case the stability is with respect to the rotation, not with respect to the y direction. Clear? So 0.602 is the answer. मान लो कि अगर आपने इस चीज को निग्लेक्ट नहीं किया तो अभी आपको काफी कम चेंज आएगा, maybe in the third decimal things can change, that's all, okay. But since here it's given the dimension of length is very large compared to the diameter of the ball, so compared to the buoyancy on the wood, the buoyancy on the ball is very small, okay. Did you all understand why sigma fy you cannot balance in this case? Few more component was 13.85, बाकी सब बड़ा टाइम है. Yeah, of course the remaining terms would be very large compared to the previous things. उज्जवल, उत्सव, पांडव, ऐसा मत करना, ठीक है. Anyone can ask any doubts. अगली बार ऐसे मत करना उत्सव. Fine? And I'm sorry प्रशांत. चलो, let's solve this. ये क्वेश्चन काफी टेक्स्ट बुक्स में होते हैं. Any book you open in fluid mechanics, Frank and White, Tengel, Munson, you open any book, you can see this. चलो, air entering a tube at section 1 and exiting to the atmosphere at section 3. At section 1 and 3 diameters are 5 centimeters and at section 2 it's 3 centimeters, okay. The required mass flow of air to suck this water up to 10 centimeters into the section 2 will be dash kgs per second. So what should be the mass flow rate of the air such that this water can be sucked? So you can understand one thing, why water can be sucked up, that's the question, okay? Because when air is flowing at some mass flow rate, when you reduce the cross section, the velocity, the kinetic head increases, okay? Velocity will increase. So what happens to pressure? This will come down in the flow, correct? So when the pressure here is coming down and here the pressure is high, then definitely fluid can move up. Yes? Can you understand this physical concept? It's very simple concept. When this fluid is flowing, then if you narrow the cross section, then the velocity increases, and at this location the pressure at section 2 falls, okay? So when pressure at section 2 is low and pressure at this point is high, the fluid can have head defense and it can flow like this, okay? Conceptually we'll look at the maths and equations later, but conceptually pata hai ki why fluid can move up? सबको कॉन्सेप्ट क्लियर है या नहीं? पता चला कि फ्लूइड क्यों ऊपर जाता है? या we'll look at the maths, no issues, okay? So let's solve this. Then this is section 1, and this is section 2, of course. Then if this water has to rise till this point and it's just reaching such that it don't have any kinetic energy, it's just reached, then the air is taking it, okay? So if you look at the pressure difference between these 2 points, this is again open to atmosphere, so P atm local, and here also the pressure is P atm local, it is discharging to atmosphere, okay? So P2 plus rho water G into this 10 centimeters, which is 0.1, this should be equal to P atm local, correct? So which tells you this P2 minus P atm, or P2 can be written as P atm local minus rho W G into 0.1. So this is what you get. It's just lifting up by that amount, okay? High pressure to low pressure, so there is head difference, इसके वजह से fluid ऊपर जाए ट्यूब से. So P atm minus rho W G 0.1. Now let's see what should be the mass flow rate. So अगर आपको mass flow rate calculate करना पड़ेगा तो you can calculate A1 V1 ρ1, A2 V2 ρ2 and A2 A3 V3 ρ3. And let's assume incompressible flow, क्योंकि if you look at these diameters 5 centimeters and normally if you calculate the velocity sample at this point for 10 centimeters height, ये काफी छोटा values है. Normally you'll have incompressible flow. So let us take density common. See, yesterday's class में मैंने बताया कि incompressible fluid अलग होता है, incompressible flow अलग होता है, ठीक है? From where the 10 centimeters is measured, sir? From this, because that's the level which water is lifted up, ठीक है? Now let's see, incompressible fluid अलग होता है, incompressible flow अलग होता है, ठीक है? So when you write Bernoulli's equation, if you apply 2 points, at 2 points if the flow density is not changing, then the flow is incompressible flow, okay? Even a fluid which is compressible can undergo an incompressible flow, and even an incompressible fluid can also undergo a compressible flow, ठीक है? Depending on the velocities and the Mach number. जब अब मैंने compressible flows पढ़ाता हूँ आज, so मैं पूरा डिटेल में देता हूँ, ठीक है? So if you see m dot पता चलना है हमको, so m dot is equal to ρ1 A1 V1, or it can also be equal to ρ3 A3 V3, of course, ठीक है? Then assuming incompressible flow, क्योंकि temperatures कुछ नहीं दिया था, so normally if you have incompressible flow, so ρ1 ρ2 ρ3 ये सब सेम ही होगा. So this implies d1 square v1 is equal to d2 square v2, of course, okay? So at section 1 and 3 are 5 centimeters and diameter at section 2 is 3 centimeters, okay? So यहाँ 5 and 5, it's a venturimeter, so obviously it should connect back to the pipe and you should have diameter here, so which is equal to d3 square v3. But since d1 square and d3 square are same, okay, so v1 should be same as v3, of course, from the continuity, yeah? So v1 is equal to v3 anyway, because d1 is same as d3. So let's see, applying Bernoulli's equation, at section 2 and 3, or at points, let's say you take a point here, you call this A and you call this B, for example, which is just open to the atmosphere. So at A and B, so this gives you P2 by rho g plus V2 square by 2g plus Z2 is equal to P3 upon rho g plus V3 square by 2g plus Z3. Okay, so there is no friction much. So because dynamic viscosity कुछ values नहीं दिए थे, so we'll assume there is no friction as of now. So it's a horizontal pipe, so there is nothing that you have. P2 minus P3, so P3, this is discharged to again atmosphere. Question में दिया था कि the fluid is discharged into atmosphere again. Okay, so you can see exiting to the atmosphere at section 3. So यहाँ जो pressure होता है वो P ATM ही होगा. So P2 minus P ATM, P2 minus P ATM local by rho fluid into G. Okay, you can say rho fluid into G is equal to V3 square minus V2 square upon 2G. Correct? So V3 square minus V2 square upon 2G. So let's see what would be PA2 minus PATM. You see, P2 minus PATM local by rho g is equal to minus 0.1. Okay, so that's minus 0.1. So इसका मतलब यह है कि इस term का value होगा minus 0.1. What's the difference? What's the relation between V3 and V2? Again, go for this continuity equation. So V2 or V3, you can say whatever. V2 is equal to D3 by D2 whole square into V3. So V2 is equal to D3 upon D2. So this is 5 and this is 3 centimeters. So 5 by 3, which is 25 by 9 here. V3. So that's how you have the velocity relation. So if you substitute here, you'll get V2 or V3. Then just by multiplying density into area, you can get mass flow rate. A very straightforward thing. Okay, it's a simple Bernoulli's equation and a continuity equation. That's all. So let's see. If you solve this, then इस क्वेश्चन XC में not exactly the same question, but ऐसा ही क्वेश्चन आया था. So minus 0.1 into 2G is equal to V3 square minus V2 square. So V3 square times of 1 minus V2 square. So V2 square होगा कि square of the 625 by 81. Okay, so you'll get V3 in some meters per second. So if you get V3, anyhow V3, V2, you can calculate any one. So m dot is equal to density of air 1.205. Since you'll get V3, so pi by 4 D3 square, which is 5 centimeters into V3. So we'll calculate and get the value of m dot in kgs per second. That's all. Fine. So let's see. First calculate this V3, then substitute here and multiply. Okay. So V3 square minus 0.2 into 9.81 minus 0.2 into 9.81, so minus 1.962 divided by 1 minus 625 by 81. Okay, so this is the value and square root of that 0.5404 049, so 0.5405 0.5405. Okay, get this value into 0.05 square. Okay, so into 0.05 square into pi by 4, so into pi by, okay, into pi is not done, so into pi by 4, good, into 1.025 0.00127 kgs per second. Is it 0.54? If we can put PATM equal to 0, then Can you please repeat the difference between incompressible fluid and incompressible flow? I'll repeat. Okay. 0.54. Right? Is this 0.54? Yeah, this is 0.54. This is the velocity at section 3. Okay. So density into area into this velocity. So let's calculate again. 0.5405 into 0.05 square into pi by 4. Okay, into pi by 4 into 1.205. 0.00127 kgs per second. So for 1 second to the centimeters gap, this much amount of air is flowing in. Okay, 0.00127. Yeah, 127 of course. Okay, that's all. The only calculation you should do is this. Other than this, everything is physical. By just understanding certain physics, you can come up. Okay. So first, I have done small amount of analysis to make you understand why fluid lifts up. Then the continuity equation and the Bernoulli's equation will give you the answer. So 0.00127 kgs per second of air is flowing through the pipe. Okay, such that the water can be lifted by 10 centimeters. Clear? ऐसा question एक बार XC में आया था, but of course it's not a tough question actually. Only the equations look little big. These are the two calculations. That's all. Okay, let me have some water meanwhile. So are you all okay with this question? अगर किसी को conceptually doubts है तो पूछ लो. कैलकुलेशन इज द मेन पार्ट. कैलकुलेशन के बाद कॉन्सेप्ट भी आना चाहिए. ओके, नहीं तो दिक्कत होगा. Just a second guys, this chart has again gone up. I should put this in a one then. Okay. Hi Prakash, how are you? So how you put P3 to PATM? It's given the fluid is getting discharged to atmosphere. Okay. So इसके लिए जहां जो सेक्शन 3 का प्रेशर है वो PATM ही होगा. Okay. The pressure difference will lead flow through the pipe. Yeah, of course. Okay. And this is a very common question in any textbook. Round off to 3 decimal places. Sorry. So if you round off to 3 decimal places, 0.001 kg per second. That's all. Okay. So it's almost like 1 gram per second of air is flowing. We'll click with concepts, but due to no proper attention to calculations, will lead to negative marking. Correct. सर जी FM एंड डर्मो के टॉपिक एंड सब्जेक्ट वाइज टेस्ट में लाइक 60% मार्क्स आ रहा है, तो इज इट गुड? कैलकुलेशन मिस्टेक कब है क्या? इज दैट कैलकुलेशन मिस्टेक्स नहीं करना चाहिए प्रकाश, एंड क्वेश्चन को मतलब थॉरोली रीड करना पड़ेगा. कभी कभी क्या होता है, क्वेश्चन हम ओवरलुक में करते हैं. लाइक आज मेरा टेलीग्राम ग्रुप में एक बंदा ने कमेंट किया था कि एक जगह पे क्वेश्चन में दिया था कि किलो जूल्स यूनिट्स, लेकिन ओवरलुक में मैंने रीड किया कि किलो जूल पर केजी. ओके, सो दिस काइंड ऑफ थिंग्स हैपन. पहले क्वेश्चंस को ओवरलुक मत करना, आराम से मतलब स्लोली सॉल्व करो पहले. दूसरा चीज़ ये है कि कैलकुलेशन मिस्टेक्स. ओके, कॉन्सेप्ट सबको पता है, सबको पता है कि ये होगा बर्नौलीज इक्वेशन, लेकिन जब यहाँ तक आता है लोग गड़बड़ कर सकते हैं. ठीक है, आई डोंट वांट टू डू दैट. सो इसलिए जब क्वेश्चंस मैंने सॉल्व करता हूँ उस टाइम पे कैलकुलेशंस को इक्वल इंपॉर्टेंस दे सकता हूँ. ओके, क्योंकि मुझे पता है, यू नो, if those calculation mistakes are not there, I missed all India rank 1 almost like 2 times, or yeah 2 times I missed because of calculation mistakes. ठीक है, तो calculation mistakes के चक्कर से 10-4 यहाँ वहाँ घूमे मैं. ओके, सो आई नो द इम्पोर्टेंस. इसलिए अगर आपने एक चीज़ नोटिस किया तो भी जब मैं क्वेश्चन सॉल्व कर सकता हूँ, आई शो यू द कैलकुलेशन इन दिस कैलकुलेटर. ओके, क्योंकि एग्जाम में इस कैलकुलेटर यूज करना पक्का आना चाहिए. तो फुल लेंथ टेस्ट में 55 आ रहे हैं एवरेज. इज इट गुड? और 10 मार्क्स इंप्रूव करने की कोशिश कर लो. ठीक है, फाइन, क्योंकि 65 सेफ जोन ही है. सो 65 मार्क्स आए तो पक्का 300 से नीचे आएगा रैंक. यू विल गेट एनीथिंग वॉट एवर यू विश फॉर. ओके इस कैलकुलेटर यूज करना काफी इंपॉर्टेंट है, ठीक है। या मैक नंबर वाला नॉर्मली पेड बैचेस में काफी टाइम होगा, मतलब कॉम्प्रहेंसिव बैचेस में, सो तब मैं ये सारी चीज बात कर सकता हूँ, लेकिन अभी फटाफट सॉल्व करना पड़ेगा इस क्वेश्चन, ठीक है। दामा का मैक नंबर वाला, हाँ ऑफ कोर्स आई डू ऑल दिस मिस्टेक्स बट कैलकुलेशन वाइज नॉट कॉन्सेप्चुअल थिंग्स, ठीक है। सो कैलकुलेशंस काफी इंपॉर्टेंट है। प्रकाश एक ही चीज कर लो, लाइक जब क्वेश्चन सॉल्व करते हैं आराम से क्वेश्चन पढ़ लो पहले, ओके, एंड देन डोंट डू द कैलकुलेशन मिस्टेक्स, ठीक है। 40 मार्क्स इन मार्क्स, हाउ टू इम्प्रूव सर। नॉर्मली आपने जो कॉन्सेप्ट ऑलरेडी पढ़ा था तो उस कॉन्सेप्ट को रिवाइज कर लो पहले। दूसरा चीज है कि कैलकुलेशन मिस्टेक्स, अगेन आई एम टेलिंग यू कैलकुलेशन मिस्टेक्स होता है बिकॉज एवरीथिंग इज पार्ट एंड पार्सल ऑफ द एग्जाम, बट लेकिन मिनिमाइज करना पड़ेगा, ठीक है। इट्स स्टैग्नेंट, जो कॉन्सेप्ट्स आपने ऑलरेडी पढ़ाया था उसको रिवाइज करके दे दो टेस्ट, ठीक है। बिकॉज ऑल दिस 10-15 मार्क्स विच यू वांट टू इंप्रूव आफ्टर द एग्जाम, इफ यू सॉल्व द पेपर यू विल गेट दोस 10-15 मार्क्स, लेकिन एग्जाम की टाइम पे गड़बड़ कर सकते हैं, ठीक है। सबको होता है कि अरे भाई इस और एक 10 मार्क्स करना पड़ेगा और एक 15 मार्क्स करना पड़ेगा, ओके, बट आफ्टर द फिनिशिंग ऑफ द एग्जाम इफ यू सिट पीसफुली एंड इफ यू सॉल्व द क्वेश्चंस वो 10-15 मार्क्स मिलेगा आपको। एग्जाम की टाइम पे नहीं कर सकते हैं क्योंकि प्रेशर की वजह से कैलकुलेशन मिस्टेक्स, जो कॉन्सेप्ट्स आपको ऑलरेडी आते हैं वो स्ट्राइक नहीं हो पाएगा, सो दिस थिंग्स हो जाएगा। डिनर ब्रेक मिलेगा क्या? आए 4 घंटे की क्लास में डिनर ब्रेक चाहिए क्या आपको? खत्म कर सकते हैं, ठीक है। मैथ्स में प्रॉब्लम होता है, ठीक है। मैथ्स में क्या करेंगे अब इस टाइम में बताओ? कोई दिक्कत नहीं, लाइक जो टेस्ट सीरीज का क्वेश्चन आ रहे सो वो सॉल्व करो, अगर नहीं हो पाएगा तो देन प्लीज लर्न हाउ टू सॉल्व दोस क्वेश्चंस, तो फाइनल एग्जाम में इतना दिक्कत नहीं होगा, ठीक है। फाइन, कॉम्प्लेक्स से डर लगता है, कोई दिक्कत ही नहीं है। फ्लूइड एक्चुअली जो लोग कॉम्प्लेक्स नंबर्स चाहिए वो मैं इंग्लिश बैच का लेक्चर्स अपलोड हुआ था इंग्लिश चैनल में। फ्लूइड मैकेनिक्स में पोटेंशियल फ्लोस पढ़ने से पहले मैंने कॉम्प्लेक्स नंबर से ही पढ़ाया था, सो फर्स्ट लेक्चर में थोड़ा सा कॉम्प्लेक्स नंबर्स का इंट्रोडक्शन देता हूँ, ठीक है। तो सब कल लास्ट में सर इंपॉर्टेंट बता सकते हो सर, एंडिंग ऑफ लेक्चर फॉर मैथ्स, ठीक है, ओके। विल टेक मैथ्स महायोजन? नहीं, एक्चुअली पुनीत सर लेते हैं इस बार, क्योंकि मैं हिंदी उतना अच्छा कंफर्टेबल नहीं है मैं, तो पुनीत सर भी ले सकते हैं। तो ठीक है, आज सेशन की लास्ट में मैं मैथ्स कैसे रिवाइज कर सकते हैं और हाउ टू अटेम्प्ट द क्वेश्चंस एक थोड़ा सा 5-6 मिनट्स का सेशन देता हूं, ठीक है। दिस इज नॉट क्वेश्चन एंड आंसर सेशन, ओ माय गॉड, ओके फाइन, चलो। लेकिन उससे क्लैरिटी नहीं हुआ तो इट इवन इफ यू सॉल्व सम 100-150 क्वेश्चंस इट विल not be good for all the candidates, okay। चलिए solve this question. The velocity field in Cartesian coordinates in a 2D study incompressible flow of a fluid with densities rho is V is equal to 3x I bar plus 2y j bar. Assuming no body forces, the magnitude of the pressure gradient at the point 1,1 is alpha times density. The value of alpha is dash. So let's see how to solve this question. Solution. The velocity field in Cartesian coordinates in a 2D study incompressible flow field is, so given the velocity field is equal to 3x I cap plus 2y j cap, ठीक है। So u is 3x and v is 2y. Assuming no body forces, magnitude of the pressure gradient at the point 1,1 is this, okay। So let's see Navier-Stokes equation for incompressible flow. So rho x bar minus del p plus mu del square v is equal to rho times dv upon dt, which is acceleration, ठीक है, and no body forces, then inviscid na flow of a fluid with density, there is no information about viscosity, so this is 0, inviscid flow. So minus del p is equal to rho times dv upon dt actually. Okay, so if you take the magnitude, both are vectors. So अगर आपने magnitude लिया तो, so magnitude of gradient of P is density into magnitude of dV by dt, and this is given as k times or alpha times rho. So what is alpha? Therefore alpha is magnitude of acceleration at the point 1, 1. That's all. Okay, so 1, 1 point पे acceleration vector निकलो and calculate the magnitude. That's all होगा. So then if you want ax steady flow, so u into dou e by dou x plus v into dou e by dou y, कुछ नहीं है. ay is equal to dou v by dou t plus u into dou v by dou x, nothing, v into dou v by dou y, that's all. So 4y. So this implies at 1, 1 acceleration vector is 9i plus 4j. Okay, 9i plus 4j. So alpha is magnitude of 9i plus 4j, which is 81 plus 16 root 97. 9.85 is the value of alpha. Okay, correct. 13 आ गए. 13 कैसे आए? मैंने कुछ गड़बड़ किया? इस दोनों को ऐड मत करना भाई, ठीक है? Magnitude of the vector is not sum of the components, correct? Root of fx square plus fy square वो कैलकुलेट करना पड़ेगा. Magnitude of the vector, correct ना? 13 आने के लिए इस दोनों को ऐड करना पड़ेगा, लेकिन वो magnitude of the vector नहीं होगा, ठीक है? If that's the case, life would have been very easy. Why using Navier-Stokes equation? That's the general momentum equation, correct? पहले normally let's write the general momentum equation, and from there if what are the terms are not there, make them 0. That's all. Clear? Because Euler's equation is subpart of Navier-Stokes equation. So root 97 is correct, sir. 97 square root, yeah, correct. 9.85. ठीक है? Clear? So let's go to the next question. So let's see. An accelerometer is made from a liquid filled U-tube manometer as shown in the figure. The expression for the liquid level difference H caused by an acceleration A in the terms of tube geometry and fluid properties is dash. So let's see. You have this tube and you have L and you have this H. Clear? So that's the difference. Square root of 97 kaisa hai? This is the vector. Okay. So if you take magnitude of this vector, root of 81 plus 16. Okay, that's all. Clear? So you used mod and then square it. Okay, see, even if you have negative, the magnitude of the pressure gradient would be nothing but this. Okay, so even if you have these things, that would still give the same. Okay, because it's magnitude. Okay, that's why. Chalo, let's see. This U-tube is accelerating at some acceleration A. Then there is a difference in the limbs. Okay, and this limb difference is H. So what is the acceleration? The expression for the liquid level difference H. So this H in terms of L, A, G, everything. Okay, so let's see if you connect these 2 points. The difference between these 2 points is H. H. Okay. So if this is the angle theta, for example, then tan theta, which is acceleration by G, which is also same as H divided by L. Correct? So H should be A into L upon G. That's all. A very straightforward question. Okay. Just connect the 2 points in the limb. So the pressure variation is accordingly such that we have tan theta. कुछ लोग ऐसे भी कर सकते हैं, they will take this midpoint, okay, they will take this midpoint and they will tell you in a length of L by 2 this difference is h by 2, दोनों सेम ही होगा, h by 2 by L by 2 or h by L is same, okay, so directly you can take the ratio, no issues. Yeah, rigid body motion. So if the tank is accelerating, then you can get the acceleration using this techniques. Okay, so let's move forward. Consider study incompressible and uniform flow through the device shown. Okay, so there is a device which is shown. So A1 V1, A2 V2, A3 V3. Of course, the magnitude of volume flow rate through section 3. So what is the volume flow rate Q3 through this section? That's what you want. Okay, so very easy question, but they can ask you for 1 mark kind of stuff. So let's solve this. So this is a steady control volume. So if you have a steady state control volume, fine. So for steady state, sigma m dot in should be same as sigma m dot out, and this can be written as density times sigma q in is equal to sigma times density, sorry, discharge q out, and this is for incompressible flow. That's the density is not changing as you move. Okay, so incompressible flow. So what are the all points where fluid is going in? There is only one inlet, which is section 1, and outlets is 2 and 3 outlets. Okay, so what is Q1? Discharge. So you see this area is perpendicular to this velocity, so directly you can write 0.1 into 3, or let's say A1 V1, A2 V2 plus A3. Anyway, we need just Q3, the discharge through this. So Q3 is A1 V1 minus A2 V2. You can apply these formulas only when velocity is perpendicular to the area. It's perpendicular at both the cases. So A1 V1 0.1 into 3 minus A2 V2, so 0.05 into 10. See, this is where I do calculation mistakes. Okay, I know that 0.05 into 10 is going to be 0.5. So instead of writing this, I'm planning to write 0.5 into 10. Okay, because one step forward I have taught. So these mistakes you should avoid. Okay, so Q3, this is 0.3 minus 0.5. So minus 0.2 is what you are coming. Means the fluid is actually coming in. The magnitude of the flow rate through section 3. Okay, so that means the fluid is actually coming inside, and these two together are going out to this. Okay, so this is Q3. So the magnitude, okay, so Q3 in this case is minus 0.2 meter cube per second. So what's the meaning of negative sign? So this tells you Q3 we have taken as out, but Q3 value has come negative, so which means negative sign signifies flow is inward. Flow is inward. Okay, so 0.2 meter cube per second flow is going into the control volume. Okay, we got a negative sign because we misjudged that this Q is going out. If velocity is not perpendicular, in that case how to find discharge? M dot is equal to rho times integral V dot n cap dA. Okay, so this gives you M dot is equal to rho V cos theta times area, and this theta is angle between normal to A and V. Okay, that's how. Resolution is what you should do. No, it's just maybe some hoses are connected, whatever, so that the flow inside the control volume is maintained constant. Okay, means the amount of flow, amount of fluid at any point in the control volume at any given point of time is fixed. Okay, is this clear to all of you? It can be anything by some source which is not in your business right now. Maybe some hoses are connected, whatever, fluid is coming inside to this section. Okay, can you check the calculation once more? Calculation once. 0.1 into 3 is 0.3. 10 into 0.05 is 0.5. So if 0.3 is coming in and 0.5 is going out, then definitely 0.2 should come towards this. Okay, Maniman, I think the calculation is correct. It's a straightforward. 0.1 into 3, 0.3. 10 into 0.05, 0.5. So 0.3 is going, 0.5 is coming, which means 0.2 should go inside. So it is 0.2. Around to 1 decimal place, straightforward. 0.2 meter cube per second. Okay, after solving every question, please check the units. Okay, it's very important. जब आप आंसर एंटर कर सकते हैं उससे पहले यूनिट्स चेक करना जरूरी है, क्योंकि इतना सारा कैलकुलेशन करने के बाद अगर यूनिट्स की कन्वर्शन से मार्क्स गए तो विल फील वेरी बैड आफ्टर द एग्जाम. चलो, लेट्स सॉल्व दिस. Water flows steadily past a porous flat plate. Okay, so water is flowing steadily to this porous flat plate. There's a flat plate and there is some pores here. Okay, so there is some pores. So water flows steadily past a porous plate. Constant suction is applied along the porous section. Obviously there is a flow, and here this velocity is given. V is equal to minus 2 J mm per second. Width of the plate is 1.5 meters. Width is 1.5. The velocity profile at section CD. So at this section CD, you have some velocity profile because of the boundary layer, which is u by u infinity is 3 y by delta minus 2 y by delta whole power 3 by 2. The mass flow rate across the section BC is dash. So what is the mass flow rate across the section BC? But BC is not there. I think it's AC. Okay, so please change this. This is AC. So this would be the AC. Okay, so I think that's what you have. The velocity, mass flow rate across section BC, but BC doesn't have any section. So I think, yeah, this is what you need, AC. Okay, so let's see, it's a PYQ. It is a PYQ. PYQ has section. Thank you. Sorry, I can't pronounce your name. Kinu. Okay, sorry Kinu, but thanks. Okay, you have a PYQ where you have suction to the plate. ये क्वेश्चन बढ़िया से समझेगा. इस टाइप में कंफ्यूजन होता है. ठीक है, ओके फाइन, आई विल स्पेंड सम टाइम. बट इज दिस क्वेश्चन इन PYQ? आई डोंट रिमेंबर इट्स इन PYQ. PYQs में this there is no suction, it's a fixed plate. Okay, then anyway, let's see. Not same question, no? Thanks Adarsh. Are you joining in this sir? पहले ऑफर लेटर आने दो, तब डिसाइड करेंगे. Okay, actually as for some information, one of the persons has called ISRO in my lab, so he's a 1 year early passed to me, but it was fixed at base. Okay, but here base has a suction. Okay, so I lost my original Aadhaar card which upload on gate form, but I print out color print. Is it valid? Yeah, you print it. Okay, cut the bottom part and get it laminated. That's all, it's allowed. Okay, you can print, no, print it, print a color print, cut the bottom part, or even full part you can laminate, but you can laminate the bottom part, it's okay. Okay, you can take, nobody stops you. Or else you can take your, okay, you have filled the Aadhaar card details, no? Okay, you can carry the Aadhaar card. Chalo, let's solve this. So at steady state, so if you look at steady state, in this volume the amount of fluid should not change. Okay, so let's see. Solution. This is the velocity profile at this section CD. So M for steady state operation, of control volume for steady state operation of the control volume. So you have m dot AC, whatever the fluid that is entering through this section, m dot AC, that should leave to BC, sorry, not BC, this is what is the section, AD plus CD. Okay, m dot CD, of course. Okay, so this is m dot CD. Talk to you personally, please. Okay, Kino, no issue. You can maybe like tomorrow you can call me in the Telegram. Okay, because today raat hoga, obviously by the time this session ends. Just message me, I'll call you tomorrow. Okay, before I go to the conference again, I'll call you. Chalo. So what we are doing? Yeah, mass balance. Okay, so whatever the mass that's entering through this should leave either to this face or this face. Okay, and you have the velocity profile here. So m dot AC, which is what you need, m dot AD. So what is the mass flow to this plate? There's a suction at this plate. Normally we do this in case of heat transfer analysis a lot, okay, in the thermal boundary layers. But anyway, so this is 2 mm per second. Length of the plate is 2 and width is 1.5. So if you observe, the fluid is coming perpendicularly down and the area perpendicular to this would be the area of this plate. Okay, so the area means the mass which is coming out is density of air into 2 mm per second. So this can be written as 2 into 10 power minus 3 meter per second into the area. So 2 meters into 1.5. So 2 into 1.5. So rho AV plus m dot CD. So at this CD you have the velocity profile. So U is nothing but U infinity into these quantities. So integral, first you add the small amount of mass, density into U into elemental area. So what is elemental area? If you take this as dy, so dy into W gives the flow area. Okay, and let's see if you simplify this, m dot AC is equal to density, you can take out common from C to, this is from D to C, of course. Okay, from D to C. So let's see if you take density common, which is fixed value, 4 into 1.5 is 6 into 10 power minus 3, 0.006. Okay, plus integral density you have taken common, U. So what is the U at this section? U infinity into, so U infinity into 3 times y by delta minus 3 times y by delta minus 2 times y by delta whole power 3 by 2. So 2 times y by delta whole power 3 by 2, of course. Okay, so that's the U velocity profile you have into dy into width. Width is constant, which is 1.5 meters. Then in this integration you have only one variable. So y is equal to, this type of question was there in PYQ. Okay, this type. Okay, but in that case I think there is no bottom suction. Okay, chalo, let's see, y is equal to 0 to y is equal to delta. Those are the limits of integration, correct? So these are the limits of integration, because y can go from 0, because this is the y axis, so y can go from 0 to delta. U infinity at this point is 3 meters per second and delta is 1.5 mm. You have everything. Let's do this. Okay, so delta is known, so delta, okay, TK, let's do it in terms of delta. So m dot AC is equal to, density दिया क्या कहाँ, density density nothing. So water, fine, so 1000, let's take 1000. So 10 cube into 0.006 plus U infinity is constant, so U infinity is 3 meters per second. So 3 into, okay, so 3 into integration. So what 3 into that 1.5 is also constant, you can bring it out. So 3 into 1.5, 4.5, 4.5 into, so if you integrate this, 3 by 2 y square by delta, so within the limits you have a delta, minus 2 into integration, so 2 by 5 into delta power 5 by 2. That's all. Okay. So you have delta power 5 by 2. Is it y delta power 3 by 2? So sorry, just a second. I think here we should not mess up. Delta. That's all. Okay. So just an integration, single variable integration. You do carefully. So 3 by 2 delta minus 4 by 2 into 2 by 5. Yeah, I think this is correct. Okay, that's all. This is the value. So let's simplify. M dot AC is 10 cube 0.006 plus 4.5 times of 3 by 2 minus 4 by 5. So 3 by 2 minus 4 by 5. So 15 by 10, 8 by 10. So 7 by 10 total. Okay. So this is 7 by 10 times of delta. So what is delta? Delta is given 1.5 mm. So if you convert to meters, 0.0015 meters. So finally this m dot is going to be kgs per second. Okay. So this is kgs per second. So let's do the calculations. 7 into 0.0015. So this value divided by 10 into 4.5. So 0.004726 plus 0.0006. Okay, 0.1017 into 1000. So 10.725 kgs per second. It's a perfect value, 10.725. Okay. Clear to all of you? 10.725 kgs per second. Can we do by finding average velocity? Of course you can do, but even to calculate average velocity you should do the same integration. Okay, that doesn't simplify the question. ठीक है, अगर मान लो कि आपने एवरेज वेलोसिटी से करना तो भी you have to calculate the average velocity using this integration. Discharge by area. Okay, even then everything mathematical complexity remains the same. And mathematically complex भी नहीं है, single variable integration करना पड़ेगा बस. Sorry, 4.5 कैसे आया? 4.5. This 3 u infinity is 3 meters per second. And this width is 1.5. So 3 into 1.5 is this 4.5. Okay. No, Sharma, you have done some calculation mistake, hopefully. Okay. Because even if you do the concept using average velocity, you would get the same answer. Okay. Chalo. So let's go to the next question. Solve this question. A tank of water sits on a cart with frictionless wheels. Okay, so there is no friction here as shown in the figure. The cart is attached using a cable to some mass 10 kgs. The coefficient of static friction of the mass with the ground is mu equal to 0.55. So the friction at this mass is 0.55. You just ignored velocity, but you have to consider this, no? Okay. So if the gate blocking the tank, so there is a gate which is blocking the tank, so this gate is removed. The value of mass m, because कल एक बंदा ने पूछा था कि सर cos theta sin theta वो components नहीं है क्या? So in this question we'll use. So the value of mass m, that is just sufficient to hold the tank in place. So if you take this, so first let us look at the physics. Okay, why you need some mass to stop the cart? If you take this gate, from this cart the fluid will, from this tank fluid will exit, correct? If fluid is exiting in this direction, then it has some x component, and because of which as a reaction force this tank will try to move towards left, correct? Yeah, yes. Physically if you lift the gate, then fluid will move. As a reaction force the cart will try to move left. Okay, so if cart is trying to move left, if you want to keep the cart at some fixed location, you should have some mass which holds the cart back. That's the physics of this question. We'll see the maths. Okay, we'll write some equations, free body diagram, all this stuff. But physically, you should understand why you need mass to hold the cart. Okay, then let's see. This question is normally, I have picked it from one of my paid batch classes because it's a very good question. So that's why I thought of putting it. And it has very nice chance to come in gate. Someone can ask you if they want to ask. So chalo, let's see. You take the control volume involving full cart. Okay, so this is the control volume. Okay, then in this control volume, because this cart is the thing which is moving, so if you take this as the control volume, okay, then this jet will come out with some velocity. Okay, so let's say this v is the velocity at the outlet which is cutting this control surface. Okay, then if you remove the gate, the wet jet is coming. So first let us take the free body diagram of this mass m. Okay, so if you take the free body diagram of mass m, ultimately you have mg acting and normal reaction. Then this cart will try to have some tension in the cable, so which is connected to this, so T, and since there is friction between the block, the static ground friction is mu, so you have some friction force which is mu n. So definitely you know this T, tension in the cable, is mu m g, a very straightforward thing which you do in mechanics. Okay, so and of course this is also mechanics, fluid mechanics. So T is equal to mu mg is the tension in the cart at any given point. Okay, and that tension is also applied on this. So let's take, this is positive x direction for the analysis and this is positive y direction. Okay, and this is, anyway, if you have fx is equal to 0, taking force in this direction as positive. Okay, force in the positive x direction as positive, basically like this. Then 1500 series question, I think maybe I have given, but it's a very nice question, so I want you to practice again even if you have seen it previously. Chalo. So T is equal to mu mg, of course, here 2 meters. Then let's look at the cart. Now let's apply Reynolds transport theorem for this cart. Okay, so the fluid, this is cart, it has some fluid and fluid is cutting the control surface at this point by RTT. Sigma fx on cart is equal to summation m dot v x at all inlets minus summation m dot v x at all outlets. Okay, I'm writing in minus out because I'm taking the force on the sigma fx on the cart. Okay, so sigma fx on the cart is equal to, let me write one more thing instead of this, sigma fx on cart by fluid plus sigma fx external is equal to 0. Okay, so that's what you can write. So this else it's not equal to 0 because anyway this has to be 0 because the cart is static. Okay, so this is sigma fx on the cart, so if cart has to be static then this has to be 0. Okay, so let's see what is sigma fx on the cart by the fluid. Because of the fluid leaving the cart experiences a certain force which you write by RTT. So this can be written as summation m dot v in the x direction at inlets minus summation m dot vx at the outlets, because I am taking this as my positive x axis. So there is also some external force. You see at this point there is no friction because frictionless wheels. Okay, but when you tie this string it has some tension T. Okay, so this tension T on the cart is towards positive x axis, so you have plus T is equal to 0. Is this equation okay to all of you? The total force on the cart is because of fluid solid interaction, plus you also have this tension T, that's the external force, and there is no pressure because everywhere it's atmosphere, it's open to atmosphere, so there is nothing difference. Okay, is it okay to all of you till this point? Come on guys, yes or no? Yeah, yes. किसी को कैसी डाउट है तो प्लीज यू आस्क मी इमीडिएटली. नो डाउट्स? ठीक है, इफ यू हैव डाउट्स प्लीज टाइप इन द चैट बॉक्स. सो नाउ लेट्स सी एट द इनलेट. देयर इज नो वे यू हैव इनलेट, सो this is 0. Outlet minus, there is only one outlet, and the mass which is leaving this outlet, if this velocity is v, rho a into v, and you know diameter of this section is given, so rho a v, this is the mass which is leaving, then rho a v into, now you can see if this is v, then the x component of velocity of the mass is v cos 60. Okay, and this is positive x, this is also in the positive direction, so we have v cos 60 is the velocity. There is only one outlet. Okay, normally you write summation, but here you have only one outlet actually in this case. So if you have only one outlet, then v cos theta is what you get, plus tension T is equal to 0. So from this equation you get T is equal to density a v square cos theta. So what is cos theta? Theta 60, so cos 60 is half, so T is equal to rho a v square by 2. So this tension in the cable should be equal to rho a v square by 2 actually. Okay, so then if you equate it, okay, this is one equation for tension and this is another equation for the tension. So from 1 and 2, mu m g is rho a v square by 2. So m is equal to mass which you need to hold the cart by 2 mu g. Okay, but in this complete story you don't know something. What is that? You don't know what is this velocity. Okay, so mu is given. RTT is commonly used by Professor S.K. Swami in his fluid NPTEL lectures. Yeah, of course. Okay, so anyway, if you see this m is what you have, the mass which you need to hold the cart is this mass. Okay, and in this case you don't know what is v, so how do you calculate v? Let's go for the Reynolds transport theorem. Okay, of course you neglect small pressure variations and all in this. So if this gate is removed, this pressure here and this pressure both are PATM, and this area being very large, you don't have any significant velocity here. So if you apply Bernoulli's equation at points 1 and points 2, so applying Bernoulli's equation at points 1 and 2. Okay, so at 1 and 2 if you apply the Bernoulli's equation, this is still here, I think the DTP has gone wrong, and this is still a gate. Okay, so at 1 and 2 this gap is 2 meters, so it gives you v square is equal to 2g times the height difference between these two. Okay, v is equal to 2h or v square is equal to 2g into 2, so which is equal to 4g. So just substitute here. So therefore m is equal to density into area. So what is area? This is of diameter 50 mm, so pi by 4 into 0.05 square. So this is the area of the jet, v square 4g by 2 into the static coefficient of friction is this guy 0.55 into g, that's all. Okay, so then 4 g gets cancelled, you will get mass is equal to some kgs. Okay, that's the question that you have. So let's see, pi into, and it is water, so density is 1000, you can make this as 10 cube. So 1000 into pi into 0.05 square, 7.85 by 2 into 0.55, 7.14 kgs is the amount of mass which you need to keep the cart static. Okay, and anything beyond this, you keep 10 kgs, 20 kgs, 30 kgs, the cart will still be static. Okay, but this is the threshold mass exactly at which the cart is static. Okay, did you all get the feel of doing fluid mechanics? You're doing mechanics, but where in order to do the mechanics problems, some terms are denoted with fluids. But sir, mass already 10 kg दिया है ना, 10 kgs दिया है, but 10 kgs की जरूरत नहीं है. It's just 7.14 kgs is what you need. Okay, 7.14 से ज्यादा किसी भी वेट कनेक्ट किया तो, सॉरी किसी भी मास कनेक्ट किया तो कार्ट स्टैटिक ही होगा. Okay, so to keep the cart they have put 10, but in fact you need not have exactly 10. It's even 7.15. That's good enough. These are more XE oriented questions, is it? उज्जवल, एक क्वेश्चन पता है आपको? ऐसा क्वेश्चन देखा कभी? Yes, plate, jet, spring. Here? Yes? No? This is mechanical gate PYQ. Somewhere 2000 recently, like not very old also. It's a PYQ, direct PYQ in mechanical, not in XE. Okay? And force acting on the plate, all these things are generally done by RTT. Okay? Basically, if you just see one thing, I'll take 1 minute time to show something. This is the syllabus, no? So you see, in fluid mechanics, differential analysis equations of continuity and momentum, and uske upar control volume analysis of mass, momentum and energy. Okay, that's what you have. 2021 PYQ. Yeah, maybe. Clear? You see, मैकेनिकल का सिलेबस ही खुला मैंने, ठीक है, कुछ एक्सी का सिलेबस नहीं है. Control volume analysis of mass, momentum and energy is basically the angular momentum equation. Okay, we will get, and that's the reason why these kind of questions come and people do not do and they miss. Just drop me a message, Kino, I'll call you. Okay, tomorrow hopefully around somewhere 9:30 I'll call you. Okay, solve this question. The laminar boundary layer or a large flat plate held parallel to flow is 7.2 mm thick at a 0.3 mm, 0.33 mm downstream of the leading edge. If the free stream speed is increased by 50%, then the new boundary layer thickness at this location will be approximately. So let's see. I'll give you some time. So 3 minutes. Solve this question because I'll take some break for 3 minutes. I'll have some water and it. So solve this question. Okay, so let's solve this. So we know the scaling analysis, correct? For laminar boundary layer, delta by x scales to 1 by Rex, okay? Some constant, whatever. So delta by x is scales to u infinity x by nu. So this implies delta scales to root of nu x by u infinity. So what does this tell you? Well, the same fluid at the same location, delta is inversely proportional to 1 by root u infinity okay. But now they told you if the phase stream speed is increased by 50%, okay, then the new boundary layer thickness at this location is dash, okay. So which means this is 1.5 and delta 1 is 7.2 mm. In mm, because this is in mm. So let's see, 5.878. That's all. So 5.9 you can round off. Yeah, C is the correct answer. Okay, a very straightforward question. Clear? Now let's see. Let's go to the other questions. A lawn sprinkler, as shown, has 0.6 centimeter diameter nozzle at the end of the rotating arm and discharges water at the rate of 15 meters per second. The torque required to hold the rotating arm stationary is dash. Okay, so what is the torque which you need to hold this arm stationary? Clear? So firstly, if fluid is coming in this direction and fluid is coming in this direction at 15 meters per second. For example, let's say if this is rotating, okay, I'm not holding it tight, okay. तो जो ये HMPV वायर्स है इफेक्ट करेगा क्या कुछ गेट शेड्यूल को? अभी नहीं, ओके, बिकॉज एवरीवेयर पीपल आर डूइंग गुड प्रिकॉशंस, ओके, सो डोंट वरी. तो लॉन स्प्रिंकलर क्वेश्चन मैंने इसलिए लिया था कि काफी स्टूडेंट्स को यहाँ भी डाउट होगा. सो फर्स्ट फॉरगेट अबाउट दिस होल्डिंग स्टेशनरी was of same type, okay, maybe let's see. So if you have 15 and 15 and if you are holding the sprinkler such that not allowing it to rotate, at that point you need to know what is the torque, okay. But I just want to ask you, if you leave it free, what is the direction of rotation of the sprinkler? The fluid jets are coming here and here, so can someone tell me what is the direction of rotation of the sprinkler, clockwise or anti-clockwise, about this axis? What is the direction the sprinkler would rotate, clockwise or anti-clockwise? Counterclockwise, anti-clockwise, anti-clockwise, clockwise, clockwise, anti-clockwise. It rotates. Okay, 90% tells anti-clockwise. It actually rotates clockwise. Okay, this rotates clockwise actually, because you'll see when fluid is leaving on this, fluid is leaving in this direction, so the reaction force on the arm is this, correct? So force on the arm, this is the reaction force, correct? Same will be the reaction force here, and these reaction forces are nothing but the torque, the reactions on the arm, okay. So if this arm is subjected to these two reactions, then can someone tell me what would be the direction of rotation? Clockwise, okay, because the moment is clockwise in both these cases. Clear? So if this rotates clockwise, let's say at an angular speed omega, for example, this is R1 and let's say this is R2, then This fluid is trying to come out at velocity Vj 15 meters per second, and you have R2 omega linear velocity here, R1 omega linear velocity here. Okay. Now, if this sprinkler is trying to rotate clockwise, and if you want to apply some torque, okay, if you want to apply some torque, for example, okay, then you should apply the torque in the anti-clockwise sense. Okay. So this is, anyway, this is stationary. This question can be done much easily, but I am generalizing it. Okay. So बाद में मैं without rotation भी पढ़ाता हूँ यही question. So right now, if you generalize, okay, then the reaction would have been anti-clockwise. So T external you have to apply in the anti-clockwise sense. Okay. Now let's go for RTT again. So RTT tells you sigma T on control volume is equal to sigma T on control volume by fluid plus T external is equal to 0. Why it's 0? Because this is rotating at some steady state RPM. Let's say this is rotating at some steady state RPM, so that there is no net external torque or net torque acting on the control volume actually. Okay. So this is equal to 0. Why it's 0? 0 is for rotation at constant RPM. At constant RPM. Okay. So this sigma T on control volume because of fluid, summation m dot v relative into r at outlet, v relative into r at outlet minus into at inlet, sorry, because this is on the control volume. So at inlet minus sigma m dot v relative into r at outlet, and normally we take the anti-clock sense positive, so plus the T external is equal to 0. This is what you would get. Okay. So what would be the external torque, right? So T external is equal to just summation m dot v relative into r at inlet minus summation m dot v relative into r. Sorry, this is, I am shifting it, so outlet minus inlet. So this is outlet minus inlet. Okay. So this is what you would have got. Okay. Now, can someone tell me, if this is the center of rotation, normally the sprinklers has the entry at a very small radius. So can someone tell me what is the moment arm at the inlet of the fluid? What is the moment arm at the inlet of the fluid? Means what is this moment arm, this radius r? You all remember this r is the moment arm, r cross v, from there we got that radius. Okay. So if your sprinkler is rotating about a particular hinge, and if the fluid is exactly passing through that hinge, then this radius at inlet is 0. Okay. So this r is going to be 0, and you have only one inlet term. Clear? Yeah, you have only one inlet term, so that is 0. Now what about the outlets? Let's see. So let's call this section 1. Section 2, here also the fluid is cutting the control volume, and here also the fluid is cutting the control surface. Okay. So 1, 2, 3. At 1 radius is 0. At 2 and 3, let's see what happens. Okay. So at 2 and 3, T external is equal to, this outlet can be written as m dot tangential L2 component into r at section 2 plus m dot v relative into r at section 3. I have split up. Then ultimately have two channels, so equal mass flows m dot by 2 and m dot by 2 keep flowing. Then T external is equal to, guys, just a second, let's make this as R2, R3, and R1 is here because I made sections 1, 2, 3. Okay. So m dot through the section 2 is m dot by 2. Relative velocity. So what would be the relative velocity? That's the question. Okay. So at this point, section 2, fluid is coming in this direction. This is going in the opposite direction. So can someone tell me what would be the relative velocity? This fluid is trying to come at velocity Vj. This arm is going back at a velocity R2 omega, and both are in opposite directions. So what should be the relative velocity at this cut at this control surface point. Plus V plus R omega or V minus R omega. Let's say this is Vj, okay, V for example for the time being. V plus R omega or V minus R omega. So Vj plus R omega, is it? So this actually becomes Vj minus R omega, R2 omega, okay, into R2 plus m dot by 2, same here, Vj minus R3 omega into R3. So this is the torque. You may have a doubt why it's minus. It should be plus, no, because opposite direction, so it should be plus, but it is minus because when bodies are not in contact, then the relative velocity will be plus if they are in opposite directions, okay. But if bodies are in contact, the relative velocity is difference, okay. Like for example, I always give this example. So in a shopping mall, okay, or any place, if you go by a lift, okay, let's say lift is moving up and you are in contact with the lift, okay. So if you are moving up and if you are in contact with the lift and if you are also moving in the same direction, will you reach the top easy, like fast or slow? Tell me. Your velocity and lift velocity and your velocity are in the same direction, but both of you are in contact. Then will you reach fast or slow? Come on guys, quick, tell me. Will you reach faster or slower? Lift and you are moving in the same direction and you are on the lift. So lift, you both are in contact. You will move fast, okay. That's because your velocity adds up to the lift velocity, okay. So when things are in contact, if they are in the same direction, you should add up, and if they are not in the same direction, you should differentiate. So physically what is the meaning is, when, let's say if the sprinkler arm and the fluid are moving in the same direction, for example, then if flow is coming in this direction, let's say my sprinkler is also coming in this direction, this movement of the arm, centrifugal motion, will throw the fluid more faster. Understood? So that's the physical reason why fluid comes out fast, okay. Because whenever my arm, I have certain length, and if my arm is rotating, and when my arm is rotating, the centrifugal force because of this radius will push the fluid much faster, okay. So that's why if both are in the same direction, you add up. But if that's not the case, you'll subtract, okay. So that's why there's a subtraction in this case. So this is the expression. Finally, you need to keep this machine running at constant RPM, okay. So constant RPM in this case. So torque per applied per uniform RPM of sprinkler, okay. So if you apply this torque, then the net torque on this will be 0, okay. So for omega equal to 0 in this case, for omega equal to 0, you know, T external torque that you should apply is m dot by 2 Vj into R2 plus m dot by 2 Vj into R3, that's all, okay. So T external torque is equal to m dot by 2. So what is the total mass at a rate of 15 meters per second, 0.6 diameter, okay. Density, discharge, everything is given. So m dot by 2 and Vj if you take common, so m dot by 2 Vj times R2 plus R3, that's all, okay. So you can, next chapter, when, which chapter? Let's finish these questions now. I think almost some 4 or 5 questions are remaining. So m dot by 2, which gives you rho area at each section into velocity of the jet, this divided by 2, okay. So that's the velocity. M dot is the full mass flow, correct. So then m dot by 2 is to the each section, so m dot by 2 to the mass to each section is rho a into Vj square into R2 plus R3, that's all. So it's water, density is 1000, area of cross section of each channel is how much? 0.6 centimeter diameter nozzle at the end of rotating arm. So 0.6 centimeter diameter. So pi by 4 0.6 centimeter, so 0.006, because 0.6 is 6 mm square into Vj square, 15 square into R2 plus R3. So what is R2 plus R3? 20 plus 25, 45, but that's in centimeters, so 0.45 meters. So torque is some Newton meters, and in Newton meter, they also want in Newton meter. Okay, so let's solve this question. So why you take omega equal to 0? Because of this. Okay, to keep this arm stationary, what is the torque you want? Because static condition means there are two things. One is absolute rest or moving at constant RPM. Okay, these things. And here I have done for constant RPM case, and finally I put omega equal to 0 in this case. Okay, so if you simplify this expression, let's see, 250 into pi into 0.006 square, so this value, into 225 into 0.45, 2.862, so 2.86 almost Newton meter. Okay, so 2.86 Newton meter, which 2.88, obviously the second decimal can change because of some calculations. So 2.86, 2.88, 0.02 out of 2 is like 1% difference. Okay, but did you all understand the logic of applying RTT? सर अगर टॉर्क दिया होता W पूछा तो उल्टा कर देते ना? Yeah, of course. If they give you torque and if they ask you for omega, then you have to do the same thing in inverse. तो वो नेगेटिव वाला समझ नहीं आया. See, if both are moving in opposite directions, ठीक है? Then and if the things are in contact, then the relative velocity is minus. Okay, I'll tell the example. See, let's say you have a belt, conveyor belt. Okay, and you are standing here. So let's say you need the time to move from this point to this point, for example. Okay, if this is moving and you are also moving in this direction, then since you both are in contact, the time what you need to cross these points will be very small. Okay, correct? Okay, but if this belt is moving in this direction and if you are walking back, then the time required by you to reach from here to here will be large, which means your relative velocity is small. Okay, that's all. Coming this m dot by 2, this m dot by 2 is mass to each channel. Mass to each channel actually. Okay, so if that's the mass to each channel, then mass to each channel is this. Okay, rho, here A I have put only one channel area. Clear? Fine. So solve this question. Capillary waves are generated in the sea. The speed of propagation c of these waves, it's XC question basically, is known to be a function of density O, wavelength lambda, and surface tension sigma. Assuming O and sigma to be constant, if the surface tension is doubled, then the functional form of the relevant non-dimensional group, the percentage increase in propagation speed, wave propagation speed, is dash. This question has come up in XC actually. So let's see solution. Okay, capillary waves are generated in the sea. The speed of propagation c is a function of rho, lambda, and surface tension. Okay, so this is what we have, and clearly you have a function which is depending on only three variables, rho, lambda, and sigma. So if you look at the fundamental dimensions, okay, so fundamental dimensions of c, what is c? Propagation speed, so meters per second. Density, kg per meter cube. Wavelength, L. Surface tension, okay, Newton per meter, so kg meter per second square, so mt power minus 2. So this is what we have, and right now you don't know what is the functional dependency. So let's say c is equal to some constant k into k is constant, proportionality constant, or say some constant, into say rho power A, lambda power B. Okay, let's write alpha, because you will confuse between this C and this C. So lambda power beta, sigma power gamma actually. Okay, now let's get this. Yeah, you can use Buckingham-Pi method, or you can directly use Wallis method, because only 3 variables are there. Okay, so in this case, if you equate the dimensions, wave propagation speed L t power minus 1 is equal to dimensions of density kg per meter cube, lambda L power beta, sigma m t power minus 2 power gamma. Okay, so if you equate the dimensions, this implies alpha plus gamma is equal to 0. Then L dimensions minus 3 alpha plus beta is equal to 1. Then time dimensions minus 2 gamma is equal to minus 1. Okay, so this tells you gamma is half. Gamma is half. Okay, and in fact you need not bother about alpha and beta, because rho and lambda are constants. Okay, you are not changing them. So which tells you that if gamma is 1 by 2, C is proportional to sigma power half. That's what you need. Okay, because these two things are constant. Even if you calculate using alpha and beta, that's just time consuming. Okay, but so this implies C2 by C1 whole power half. Okay, now functional form, if the surface tension is doubled, okay, so if you double this surface tension, so C2 is root 2 times C1. So the wave propagation speed increases by root 2 times. Okay, that's all. 1 by 2 comma 1. What's 1 by 2 comma 1? C2 by C1 is 1.414. What did they ask you? So the percentage increase in speed. Okay, so therefore till here it was X equation. Percentage increase in speed is equal to C2 minus C1 by initial value, it's 100. So root 2 minus 1 into 100. So 1.414 minus 1, so 41.4%. This is the increase. Correct? So the wave propagation speed increases by 41.4% roughly. Correct? Na? Because root 2 is 1.414. So root 2 is 1.414 minus 1. So yeah, 41.4% is the change. Okay. Okay, fine. I think we have reached the potential flow questions. Then meanwhile solve this question actually. Consider study incompressible fully developed flow of viscous Newtonian fluids through two stationary parallel plates in Cartesian system. Okay, everything is known to you. The origin y is equal to z is located at the center between the plates. If h is equal to 48 mm, okay, so h is equal to 48 mm. The distance between them is 2h. Such that h is 48 mm, which is like almost half centimeter. Sorry, 5 centimeters. And u max is 100 mm per second. Difference between the values of stream functions passing through y is equal to 0 and y is equal to h by 2 is dash. Okay. Okay. I'll need just few more things. Okay. Before I start this, let's look at some. Okay. So potential flows. So at this point, I'll teach you. In 2025 English batch for turbo machine, Sandeep sir solution is given in Hindi. My DPP solution is not there. Acha. Okay. So pi method भी एक बार कर देखें क्या? Okay, we'll do pi method. No. One more question of this type, sir, please. Okay, I'll give you. And 2025 English batches में turbo machine Sandeep sir solutions. Yeah, because we applicated that DPPs, I think. Okay, fine. Okay, I'll try to upload my recordings. Okay, I'll maybe just give me some 1 week time. Let this series Maha Abhyas, PYQ series and some test series is there. So let them get done. And some recordings for some other purposes are there. So once let them get done. But definitely solution steps देखने में पता चलेगा कि क्या कर रहे हैं. So but anyway, I'll try to upload my solutions. Okay. And then pi method. Okay, if you do pi method, okay, just a second. People wanted us to do some pi method. If you do pi method, oh sorry, something has happened. What are the variables? Pi method, because some of the guys are interested in this pi method. So you have C, rho, lambda, surface tension. Okay, so some function of C, rho, lambda, sigma is equal to 0. Okay, then you should choose the variables. So first of all, these things involved. Okay, so thanks Vijay. So let's see this f of C comma rho lambda sigma is equal to 0. Okay, then C is the wave speed, rho is the density, lambda and sigma. So let's see, if you look at the fundamental dimensions, these 4 variables involved 3 fundamental dimensions. Okay, so they involved 3 fundamental dimensions, okay, which are MLT. So if you look at, okay, so if you look at this number of fundamental dimensions, there are 3. So if you do the Buckingham-Python analysis, you should take 3 repeating variables, correct? Because there are 3 fundamental dimensions. So out of these 4, you pick 3 repeating variables. So how the repeating variables should be fixed? In last class I have told you, one should denote the flow geometry. Okay, so out of these 4 parameters, the one that denotes the geometry is lambda. So that will take one repeating variable. Repeating variables. Okay, so first the geometric parameter, then let's look at the kinematic condition. So kinematics basically velocity or acceleration, these kind of things. So out of this is the velocity. So you take C, and then you have 2 choices for making rho and sigma. Let's go with rho. Okay, so if you take rho, after forming these repeating variables, you should check one more thing. What's that? If you put the dimensions of these 3 variables together, okay, these 4 variables together involved 3 fundamental dimensions, correct? If you put the dimensions of these repeating variables together, L, dimensions of C is meters per second, dimensions of density is kg per meter cube. Okay, so if you check, when you put these things together, these variables should involve all the fundamental dimensions in the problem. Okay, let's say you made some choice, but let's say m is missing, t is not there in some. If you merge all these 3, then t is not there, then you have to change your choice. Okay, so let's see. Therefore the first pi term would be, you have only one pi term because 4 variables and 3 fundamental dimensions, so only one pi term is what you have. So pi 1 is equal to repeating variables, so lambda power alpha, C power beta, rho power gamma into the 4th variable is this fellow sigma. Okay, now you apply dimensional homogeneity. This left hand side is dimensionless, so it's a pi non-dimensional term. Okay, so this implies the mass units. First, gamma plus 1 is equal to 0, so gamma is equal to minus 1. Okay, then L units, alpha plus beta minus 3 gamma is equal to 0, so alpha plus beta is equal to minus 3. Okay, then for T, minus beta minus 2 is equal to 0, so beta equal to minus 2, alpha equal to minus 1 is what you get, correct? So alpha is equal to minus 1. beta is equal to this and gamma is equal to -1. So beta is -2. Okay, so let's see if you form the group pi 1, lambda power alpha, which is -1, c power beta, which is -2, rho power gamma, which is -1, into sigma. So this pi 1 corresponds to sigma by rho c square lambda. So this has to be the dimensionless term. Okay, so this dimensionless term should be equal, and if you do not change this density and lambda, then sigma by c square should be constant in both the cases, which is same as this equation. Okay, if you shift that to the other side, c square by sigma or whatever, sigma by c square has to be fixed. Okay, that's what even the Buckingham pi theorem gives you. Okay, clear? The main mistake that people do is in choosing the variables. Okay, जब आप variables choose कर सकते हैं, you should be very confident that that involves all the fundamental dimensions involved in the problem. Okay, if you miss anything, then you can't have these equations. Clear? Okay. और कोई डाउट्स है किसी को? So then, if that's clear, then let's do potential flows. Okay. So again, as I told you, XC में जो syllabus होता है वो अभी मैं cover नहीं कर सकता हूँ, लेकिन जो mechanical का important topics होते हैं, like the potential functions, steam functions, so these things we'll see and how they are connected, what's the importance. We'll look at these things and then we'll solve some questions. Okay, then I'll teach you compressible flows. Okay, it's 10 o'clock, perfect, 3 hours. Good. Maximum it will take 1 more hour, that's all. Okay, yeah, because these things are just little things for mechanical, but compressible flows कुछ important चीज है. So potential flows. Okay, so what does this potential flows mean? In some books you'll also learn this using ideal flows. Okay, so these are inviscid, incompressible, and irrotational flows. Okay, so what do you mean by this? Inviscid, incompressible, irrotational. Okay, so if you see in maths you have a very standard result that if you have a vector, okay, which I have taught in many maths batches, like, but I don't know if, how many of you are there. So if curl of any vector is 0, always that vector can be written as gradient of some scalar point function. Okay, so this implies there exists phi such that, okay, let me write the words, so many mathematical symbols. There exists a scalar function phi such that this v is given by gradient of phi actually. Okay, so always there exists some function, and that's why curl of divergence is always 0. Sorry, curl of gradient is always 0. Okay, so it happens, and this v, or basically this vector v, can be expressed as difference of some scalar point function. So what is the physical meaning of gradient? You can form a surface such that at any point, if you take normal to this is phi, correct? Normally if this is the surface, phi of xyz is equal to constant, then gradient of phi gives you normal at this point. Fine, so this is 90, and that gradient of phi is basically the velocity. Okay, now if you, for example, take 2D in the simple business, if you take 2D, for v is equal to ui plus vj, u is given by dou phi by dou x and v is given by dou phi by dou y. Okay, Can someone understand something? Streamline is such that at any point if you draw a tangent, that gives velocity. Okay, like let's say physically there is a flow, for example. Okay, if physically there is a flow, this phi is defined in such a way the normal gives velocity. Okay, if and stream function is defined in such a way that the tangent gives velocity. Okay, you know this. If stream function is defined in this way, this is psi and this is equal to constant and this is phi equal to constant. This topic is important for GATE obviously, but I'll give you some only. Okay, I understand maybe I'm a bit mathematical, but I'll just give you some key points. Okay, so how to do the things. Chalo. So understand there are two curves such that the tangent to one curve and normal to another curve are denoting the same physical quantity. Then these two curves should be perpendicular. Yes or no? Correct. Means this point of at this point of intersection, this angle should be 90. Physically, forget about all the mathematical analysis and all. We'll do that later. But physically, you'll get this. Yeah. At a point, tangent to one curve and normal to another curve are denoting the same thing, which means these two curves should be definitely perpendicular to each other. Yeah. So that's why streamlines and the lines of constant phi are called equipotential lines. Find the term surface tension. Okay. You want me to define surface tension after the complete fluid mechanics. Good. So normally if you take any surface, okay, the stretching force intensity, the intensity of the stretching force acting on a surface is called surface tension. Okay, the name itself tells you the surface, the interface will be under tension actually. Okay, why it's under tension? Because of this imbalance. You'll see there is local stretching at each and every point, and the intensity of this stretching force on the surface is called surface tension. Okay, fine. So let's see. You can also show this mathematically. This is U. We have for a stream function psi. Right now all of you know what is a stream function, so I'm not going very deep. Okay, so this is a streamline where psi is constant. Okay, so if this streamline, then along a streamline d psi is equal to 0, and this implies dou psi by dou x into dx plus dou psi by dou y into dy is equal to 0. Okay, also you know one more thing, the same streamline can be written by dx by u is equal to dy by v. Okay, so this tells you v dx minus u dy is equal to 0. Okay, so v dx minus u dy is equal to 0 of course, or else minus v dx plus u dy is equal to 0. You'll just multiply with a minus sign, doesn't impact. If you compare these two fellows, then you will understand u is same as dou psi by dou y and v is same as minus dou psi by dou x. This is in terms of stream function and this is in terms of equipotential function. And if you see, dou phi by dou x is same as dou psi by dou y, dou phi by dou y is same as minus dou psi by dou x. What are these equations? Have you seen them anywhere? U is same in both the cases. At a given point, the velocity, physically it can have only one velocity at a given point at a given time. So dou phi by dou x is same as dou psi by dou y, and dou phi by dou y is same as minus dou psi by dou x. So what can you understand from this? What are those equations? What are those equations? 𝐂𝐤𝐬 equations, correct? So these are 𝐂𝐤𝐬 equations. That's why. And you'll see one nice things about this phi and psi. Both phi and psi satisfy Laplace equation, or this equation is called Laplace equation. Laplace equation, clear? And therefore you can form something called complex potential functions, analytic function actually, exactly. So the complex potential functions, and in fact solving this potential flows in complex numbers is very easy, okay, compared to the normal classical analysis. Normally आपने कहीं भी book देखा तो potential flows के लिए काफी लंबा expressions होता है, correct? Yes. Normally if you open any potential flow books, जो इक्वेशंस आपको दिखते हैं वो काफी लेंदी होता है, करेक्ट? बट इन रियलिटी if you use complex numbers, maximum 2 to 3 steps is what you need. Normally, if some of you have attended my descriptive courses, I teach in complex numbers. So I'll teach complex numbers first for some one lecture, or at least some 1.5 like 3/4 of a lecture, and then I'll start the fluid mechanics there in that chapter. Okay, so it's very easy in fact if you use complex numbers. To some of you I have taught anyway, but right now मैं अभी complex numbers के बारे में कुछ नहीं जानना चाहता हूँ, लेकिन I just want to give you these ideas. Okay, so del square phi and del square psi both are zeros. Okay, so del square phi and del square psi is zeros. Then if you have two streamlines, for example, okay, psi1 is equal to constant, psi2 is equal to constant, c1, and let's say psi2 is equal to c2, then the difference in the stream functions, so psi1 minus psi2 modulus or psi2 minus psi1, whatever, this gives the discharge, because you know physically flow cannot cut this. Okay, so whatever the flow is in between, the same flow should continue, so therefore the discharge between the two streamlines, the discharge between the two streamlines. Actually, you opened maths notes and showed this equation while teaching fluid mechanics because we forgot. Yeah, correct. I didn't scold you, but I was sad that day because none of you remembered this, because I taught each and everything in maths for you. Correct? The normal, what does gradient tell you physically? Divergence, all these things. The Gauss divergence theorem, what does it tell you? How you apply it to physical examples? I've told you all these things in maths, but you have forgotten that day. Okay, so I became sad and I opened all my maths notes and shown you that everything is taught, but you are not studying. Okay, but at least I hope you are doing the revision now, at least. But don't forget, okay, because see, I always tell you GATE इतना complicated exam नहीं है, ठीक है? So GATE लिखने के लिए सिर्फ revision करना पड़ेगा. Okay, it's not like ज़्यादा सोचना है, then इतना logic use करके solve करना, उतना ज़रूरत नहीं आएगा GATE exam में, ठीक है? चलो. So this gives the discharge between the two streamlines in any type of flow, and so obviously you can see these two are orthogonal since phi and psi are orthogonal dy by dx of phi is equal to constant line and slope of the stream function, this is -1, because anyway you know dy by dx of phi is equal to constant is nothing but u by v, and this is minus v by u, so if you simplify you will get -1. Okay, so this is also one important result. So now this equation got painted in my mind. Okay, good. आप गुस्सा हो गए थे? No, I was not angry that day, but I was on, you know, people were not revising. Okay, so chalo, let's see. Generally I get angry very less times here. It's like almost like 1 in 1,000 case. Okay, so this is one important thing. Now many times you see the questions, they'll give you phi and ask you psi. Okay, which is even very common question in maths in complex calculus. If you have a function f of z is equal to phi plus I into psi, and this is analytic. Okay, if phi is given, calculating psi, or if psi is given, calculating phi, these questions are very, very common in this case. Okay, so by this time you might have done these questions in maths, like if phi is given, how to calculate psi, all this stuff. So the same thing. So if somewhere phi is given, you should know how to calculate psi. Okay, and many times by checking 𝐂𝐤𝐻 equations you eliminate options. That's also one way. Fine. So these are the things which generally help you. That one case, where are you from? Okay, chalo. It happens sometimes. Okay, so chalo. The flow has a velocity field given by this. The stream function psi for the flow is dash. Miller-Thomson method, yeah, of course. We use Miller-Thomson method to calculate the conjugates, harmonic conjugates. So let's solve this. V is equal to 2y times 2x plus 1 I plus x into x plus 1 minus 2y square j. Okay, so this gives you 2y times 2x plus 1 and v is equal to x into x plus 1 minus 2y square, of course. Okay, so what is the stream function for which you have these components? That's all. Okay, it is straightforward. You can do. In fact, this u can be written as dou psi by dou y, which is 2y times 2x or 4xy plus 2y. So if you integrate, psi can be written as 2xy square plus y square plus some function of x. So let's first take the options. 2xy square plus y square plus some function of x. If you check these options, there is no 2xy square here, so this is wrong. 2xy square is there. There is no 2xy square here. This is also wrong. This is also wrong. So D is the correct answer. Y square plus 2xy square plus something in terms of x actually. So if you want to get the function of x, how can you do? You can do plenty of techniques. I'll just use the common technique now. So dou psi by dou x is equal to 2y square plus f dash of x, but this is equal to minus v. Okay, so minus x square minus x plus 2y square is equal to 2y square plus f dash of x. So you multiply dx on both sides and integrate. F of x is equal to minus x cube by 3 minus x square by 2. That's all. You get this. So add it here. This is the function. Okay, that's all. Potential function. Just remember this concept, no? V is equal to gradient of the scalar function phi. That's all. Okay. So you know the gradient for scalar in Cartesian, in polar, you know everything. So it's obvious. You can calculate. Okay. This is a simple straightforward way because the velocity profiles are very simple. Until and unless there is some log or something like that, you should go for complex. That can make things easy. But for algebraic profiles, you can directly, whenever the profile is algebraic, you can just use this. Okay, fine. Solve this question. Actually, it's not a potential flow question, but still. Okay, I'll put this question in front of the potential story. Fine. So solve this question now. You know this. So solution. Consider a 2D steady incompressible fully developed flow of viscous Newtonian fluid through two stationary parallel plates in Cartesian coordinates x, y, z. Assume plates are very long in the x direction, wide in z direction. Also, there is no variation of velocity in the z direction, obviously, and distance between them is 2h. It's basically Hagen-Poiseuille flow. Okay, the velocity in such a channel is given by u equal to u max 1 minus y square by h square. The origin y is equal to 0 is located at the center between the plates. H is 48, u max 100. Difference between stream functions passing through y equal to 0 and y equal to h by 2 is dash. So let's see, you have two plates like this. Fine. Okay, then you have the coordinate system and these plates are fixed. X, Z and okay, this is Y, sorry, and this is Z, the right handed coordinate system, and this is H, plane Poiseuille flow. Yeah, so this is y is equal to 0 and this is y is equal to h. Now tell me something. If you ask me the streamlines, this is one streamline, physically there is no flow. Okay, and this is also, every horizontal line would be a streamline. Okay, so this is psi 2 and this is psi 1 actually here. Okay, if I want the difference between the difference in the stream functions, that's exactly same as the flow happening between these two lines, correct? Yes or no? So psi 1 minus psi 2 whatever is nothing but flow between y equal to 0 and y equal to h. That's what. Okay, normally you can do integrations and all stuff, but let's use some tricky things. Okay, so the discharge between across the section 1 comma 2, let's say. So this is 1 2. Discharge to 1 2 is nothing but half of the Q total, correct? So this is Q total actually. Then half of this Q total can be written as total flow area, which is 2h times width. Okay, W is the width of the plates in Z direction. Width of the plates in Z direction actually. Okay, so if you do this 2h plus W into average velocity, but average velocity can be written as 2/3 times of U max, correct? Because now we know all the techniques of this plane Poiseuille flow. Average by maximum is 2/3, all this stuff. So 2/3 of this. So if you simplify this, okay, so this discharge to 1 2 or psi 1 2, sorry, psi 1 minus psi 2 is equal to 2/3 h width into U max. That's all. So 2/3. This h is half of the width, which is 48 mm. So 4.8 centimeters into width. Okay. So what is the width actually? Okay, difference in the stream functions is per unit width, correct? So this difference, the discharge between the two streamlines per unit width. I forgot to write this. So this is per unit width. Okay, you can add this normally. So this is per unit width. So stream function. So this W is 1 in this case, because we are talking the difference of the stream functions. So this is 1. U max. So what is U max? U max 100 mm per second. Okay, 100 mm per second. So 100 mm 10 centimeters, 0.1 meters per second. So this would give you meter square per second, because meter cube per second per unit width. So it's meter square per second, and they're asking in mm square per second. Okay, good. This is dimensionless. This has dimensions. Anyway, if you get meter square per second, you can write it in mm square per second. Okay. So okay, if you want mm square, then just put everything in mm. That's good enough. Fair deal. So 48 into, this is 1 per mm into U max. U max is 100 mm per second. So this is 100 mm per second. So this gives you some value in mm square per second. So 16. That's all. 3200 mm square per second. Okay. Clear? So 3200 mm square per second is the value. Fine. Is this clear to all of you? Yes. So generally they'll ask you questions like this, where from this potential functions, stream functions, where they give phi, psi connecting velocities, like जैसे हमने पहले question solve किया था ऐसे. 𝐂𝐚𝐴 Jain, a piston cylinder arrangement contains 0.35 meter cube of air. The isentropic bulk modulus is. So you took this question yesterday. Please solve. Yeah. Our friend has one question to solve from thermodynamics. We'll solve that question. Okay. How air is assumed perfect gas in this question? The piston cylinder arrangement contains 0.35 meter cube of air. Meter cube of air at 50 degrees Celsius temperature. And 276 kilonewton per meter square. Absolute. A is isentropically compressed to 0.071. isentropic bulk modulus. So you see the isentropic bulk modulus is nothing but is compressed to this condition. Okay, so that's what you should say. Volume is changing and pressure is remain the same. Then how it's compressed? Isentropically. Okay, isentropically compressed to 0.071. Compressed. So that's why you need isentropic bulk modulus anyway. So if you have ES, okay, so this can be written as, obviously you have isentropically compression, and let's say if you deal with properties, okay, properties of point functions, so pressure, density, these things will remain the same whatever the process you go actually. So ES is equal to, like if you apply the equation, isentropic equation, so isentropically compressed, so for isentropic process, P power, or you know, basically for calculating isentropic bulk modulus, you know, 1 by rho times dP by dO under isentropic conditions. Okay, and dP by dO can be written as gamma P by rho actually here, correct? So okay, this is not the way, so gamma P by rho actually here, so gamma P by rho square I think. Anyway, let us not do the derivation, but V1 is known to you. Okay, volumes are given, so if volumes are given, then minus dP upon dV by V. So if you integrate this, 1 by V dV is equal to minus dP by ES. So you can integrate this, and for isentropic compression you have V1 power gamma is equal to V2 power gamma. So you get P2, integrate it from V1 to V2, P1 to P2. You will get ES is constant, so you will get ES from this equation. That's all. Okay. How A is assumed as perfect gas in this question? Because if you see the temperature 323 and pressure which is 276 kilopascals, definitely they are above the critical temperature of air. Okay. Normally if you look at critical temperatures of air, the values, critical properties of air. So if you look at critical properties of air, so of air, okay. So if you see engineering toolbox, generally it's like very high values, but from there we get hint that it's a perfect gas, as perfect gas has constant gamma value. No, it need not be the case, but in reality the temperatures at which you are operating, like 276 Kelvin, okay, and I mean 323 Kelvin, which is like 50 Kelvin, okay, this TR is greater than 2 in general. Normally if you see, any real gases can be assumed as ideal gases for low pressure irrespective of the temperature, and for low pressures irrespective of temperatures, and for high temperatures irrespective of the pressures. Okay, and 323 Kelvin operating range is definitely above TR more than 2. Okay, so therefore taking ideal gas behavior doesn't deviate anything. Clear? Because if you look at the, in general, if you look at this critical temperatures of things, nitrogen, oxygen, those things, it will be very small, and temperatures like 50 degrees and all, it's like working at very higher reduced temperatures. I've taught you some concept called compressibility chart, you remember? Okay, so in that compressibility chart, if TR is very small, if TR is very large, or P reduced is very small, in that case you can approximate as ideal gas. Okay, and 50 degrees Celsius is definitely more. Like normally if you see at P equal to 1 bar, so 100 kilopascals, okay, at 10 bar, okay, so at 10 bar, for example, okay, these are the enthalpy charts, but thermal conductivities. Okay, but just you figure out, you can get it. Okay, the conditions at which you are operating are very above conditions. Okay, so let's start compressible flows before we move forward. I'll again give brief insights. Okay, a very brief insight of course. Of English batch में full thermal section पढ़ाते हो. Normally I don't teach heat transfer. Okay. Use of U profile in previous question. अगर आपको वो formula नहीं पता चलता है, okay, 2/3 into U average and all, then you have to do the integration and get the discharge. Okay. But since we already know that it's 2/3 of U max, I have applied directly. But in case if you don't know, the classic way is to integrate the velocity profile. Okay, from 0 to h. Okay. Yeah. Sorry. BTD, ATD, Maths, FM. Yeah, these subjects I taught in English batches. So compressible flows. Let's see. So flows in which density variation is greater than 5%. Okay, and density variation greater than 5%. Okay. So chalo, let's see if this is 5%. Okay, so if that density variation is greater than 5%, then definitely we'll say that the flow is subjected to compressibility effects. Okay, so this density variation greater than 5% will correspond to some non-dimensional quantity which is Mach number less than square root of this is more than square root of 0.1. Okay, so we'll see the scaling analysis and all in the beginning. So if you see MA is greater than square root of 0.1 actually here, and how this 0.1 comes and all, it's a bit of small scaling analysis which I'm not doing right now at this point. Okay, normally it comes from the order of magnitude analysis. Order of dP by O is of the order of V square by 2 actually. Okay, so by adjusting bulk modulus, all this stuff, and acoustic velocity is square root of isentropic bulk modulus by density. So this gives you acoustic velocity. Acoustic velocity. Okay, and acoustic velocity is nothing but you create some disturbance in the medium, and what is the speed at which this disturbance move is called acoustic velocity or wave propagation speed in this case. Okay, so Mach number is the velocity of the object by the acoustic velocity. Like let's say if in a medium, okay, if there is a body which is at this point and this body is moving at some velocity v, okay, but because this body in its moving, it creates some disturbance, the disturbance will propagate at some velocity a. Okay, like let's say for example at this point if I snip, then what happens, this snip sound goes faster than me. Okay, in this case shockwave concept also I messed up with that. Okay, I'll cover shockwave. So if you have u, I'll do one thing, I'll take help of my notes. Okay, so that normally, because at this point of time again doing the full derivations would take so much time, so by taking help of my notes I'll write the key points. Okay, shall we do that? Normally I take 3 lectures in applied thermodynamics to cover this compressible flows, so we'll do that. Okay, because again deriving these things, because the issue is in compressible flows few expressions would be lengthy as well. Okay, so in order to tackle them you need some time, so let's not spend so much time now. So Mach number is equal to this velocity by acoustic velocity. Okay, and any flow where Mach number is greater than square root of 0.1, or generally if you look at square root of 0.1, that's 0.316 something, it will come up. Okay, 0.316. yeah, so this is implies Mach number greater than 0.316. People round it and say Mach number greater than 0.32 or sometimes 1/3, 0.33. Okay, they write a lot of stuff. So this is acoustic velocity, and a is equal to square root of es by o for any medium. For any medium. for any medium, and this A can also be written as 1 by isentropic compressibility into density. And for ideal gases, you'll see that for ideal gas, what do you see? You'll see something, no? What do you see? Yeah, A is equal to square root of gamma P by rho, or this is also equal to square root of gamma RT. So that could be the wave propagation sound. Normally I'll just show you these things just as a quick insight. In which month I have taught you applied thermodynamics? Any one of you? Recently I have taught, no, some 2 months or 3 months back. Yeah, got it. Compressible flows 1, compressible flows 2, compressible flows 3. Correct. So these are the lectures. Okay. So this is lecture number 1. So what all I taught you would be there here. Okay. So you can see, of course, that's steam turbines and all the stuff. So normally, if you want to check whether a fluid is compressible or not, you'll go for this bulk modulus, and if you want to check whether a flow is compressible or not, you go for the Mach number. That's the classification I have done here, and this is bulk modulus, which you know obviously. Then compressibility of a substance, some heat transfer, somebody asked it out. Okay, and you can see compressible flows. Okay, so this, because of the pressure difference, when there is a pressure difference, this pressure difference apply on a fluid will bring out some changes in the density of the flow in between. Okay, so if the density changes are more than 5%, then we call it as a compressible flow. Okay, which I have given. This is the order of magnitude analysis and adjusting bulk modulus and all. How this order of magnitude analysis comes is basically from the momentum equation. Okay, anyhow, at that point of time somebody has understood fluid mechanics. So if you see, that's how this complete scaling analysis and comes up, and you will finally end up with, for taking density variations as 5%, you will end up with this Mach number less than 0.32. Okay, so if a flow has to be incompressible, Mach number has to be less than this, and for a flow to be incompressible, this is the conditions, and for having flow being compressible, then more than this. Okay, more than 0.3233, whatever. So some story of satellites and all, but anyway, so classification again, subsonic, transonic, you have all these things. Okay, and so stagnation properties. Okay, so if you see stagnation properties, like if you have a flow which is moving at some velocity v, then if you bring this flow to static condition, okay, to rest isentropically. Okay, so this is rest. So this point is called stagnation point, and here the flow velocity is v, obviously. So brought to rest isentropically. So then what happens? Definitely here, if the temperature is T, density is O, pressure is P, here you will get T naught, rho naught and P naught. Okay, and in the initial cases I have taken only air being the substance. Okay, so because of thermodynamics is easy for air, that's all. So T naught, O naught, P naught are the stagnation properties. Okay, and if you see, this T naught is given by T at this point where the velocity is V plus V square by 2 Cp. Okay, and this is called the dynamic temperature. Dynamic temperature. So once you know this, then definitely this is applied from the steady flow energy equation again. Okay, a very simple technique, like enthalpy is equal to Q minus W equal to delta K plus delta P plus delta H. All this stuff, if you apply, you will get this stagnation properties. Okay, and once you have stagnation, similarly P naught power 1 minus gamma, T naught power gamma is P power 1 minus gamma into T power gamma. All this is pretty basic stuff. So P naught power P naught into rho naught power minus gamma is equal to P naught rho naught power, sorry, P into rho power gamma. So once you know T naught, and here you know these things, you can calculate T naught using this velocity. Then once you get T naught, you can get P naught, T naught, all these conditions. Okay, and you will also observe something beautiful here. This T naught, which can be written as T plus V square by 2 Cp. Okay, if I want to write this in terms of Mach number, I can write this as T plus V by A whole square into A square by 2 Cp. Okay, so this V by A is the Mach number, So T plus Mach square into A square. Like if you take the ideal gas, this is gamma RT by 2 Cp. So Cp can be written as gamma R by gamma minus 1. So T naught is equal to T, if you take common, 1 plus gamma minus 1 into Mach square by 2. So these things come up actually. Okay, so that's another way. If Mach number is given, then also you can, instead of giving velocity, if they give you Mach number for the substance, then also you can calculate the stagnation properties, and obviously once you get T naught, you can do all these things, okay, using simple thermodynamic process. Okay, and so once these stagnation properties are done, okay, that's what even I'll do, but of course I have done more formally step by step because it's a comprehensive course. So this is how you'll get from the steady flow energy equation, so the dynamic temperature, all these things, and of course the other equations. Okay, so acoustic velocity derivation, you'll see, like normally if you create a small disturbance in the medium, then that disturbance propagates at some velocity A, that's the acoustic velocity. There's a wave front which is moving, and again applying steady flow energy equation, mass balance about the wave front, you'll get this. So this is the mass balance, energy balance. Okay, so if you apply this, you will finally, it's a simple equation, nothing very complicated, hardly 2-3 steps. Okay, so if you do, you will end up with these things. Okay, and normally acoustic velocity will be more in solids compared to liquids, and more in liquids compared to gases, because the bulk modulus values first, solids, liquids, okay, and the gases, these things keep decreasing, of course. Okay, and so once you have ideal gas, see, for an ideal gas, this adiabatic bulk modulus by density converts to gamma P by O. That's what I have shown here. If you calculate this quantity for ideal gas by taking this, you will finally end up with gamma P by O or gamma RT. Okay, that's I have told you. So I think maybe till here it might be in the first lecture. Yeah, correct. So then we'll go to the second lecture where I might have talked about the area relations. Okay, so based on the flow geometry, area velocity relations. Okay, so normally if you see, if you have any area, okay, in which there is some fluid flow, you will see at any point, at any section, you'll see dA by A is equal to minus dV by V, where V is the velocity, into 1 minus Mach square. This is what the variation between the velocity and area normally. Okay, so which it's a very, again, common, very nominal relation. So if the flow is subsonic, okay, from starting, should I drop this GATE exam? Not able to understand anything from starting in the sense from where? See, I'll tell you one thing, all in one. Okay, nice name, but just put efforts. Okay, so keep continuing your efforts. There never comes a day when you see, I'll tell you one thing very openly to all of you. जब आप कॉम्पिटिटिव एग्जाम लिखते हैं, ओके, एक दिन भी ऐसा नहीं आएगा कि जब पूरा सिलेबस खत्म होता है. ओके, नेवर कम्स अ डे दैट यू फिनिश ऑल योर 100% ऑफ द सिलेबस. इतना चीज पढ़ने के बाद डेफिनेटली आई हैव टू रीड सम मोर थिंग्स. ओके, सो व्हाट एवर द नॉलेज यू हैव, with that you attempt and keep improving this knowledge. Okay, and daily you add some value to your knowledge. Within 5-6 months you will be at that level where you can clear PSUs or you can clear exams. Things come up. Okay, it's never like GATE is the only exams, you drop it, you finish it, nothing like that. It's a process. Okay, settling in exams is a process. You start it and keep moving. Fine. Maha Abhyas are generally oriented for those cases where everything is done and at the last point of time you are revising the things. But in reality, missing my gyan, I'll give some time later. Okay, I have one out in basic in thermodynamics. Yeah, I'll explain that later, Bhupati, at the end, towards the end. GATE के अलावा भी बहुत एग्जाम्स है. एग्जैक्टली, ठीक है. जब मैंने BRC निकला था, सेपरेट एग्जाम से निकला. जब मैं ISR वो निकला था, obviously so has separate exam. Okay, HPCL निकला था, separate exam. So don't worry. Okay, चलो. So this is one relation, so which tells you if flow is subsonic. Okay, for subsonic flows, this Mach is less than 1. So if Mach number is less than 1, then this is positive. So this implies dA by A is equal to minus dV by B, or you can see dA by dV is equal to minus A by V into 1 minus Mach square. Okay, and for Mach number less than 1, this full term is negative, okay, because of this minus sign. So this tells you if you want a positive change in velocity, you want a negative change in area, which tells you that if you want to accelerate your fluid, your area should keep decreasing. So in converging cross sections in subsonic flow, fluid accelerates, but whereas in case of supersonic flows, if you have a converging cross section, your fluid decelerates. That's why there comes a need of converging diverging nozzles if you want to go beyond supersonic conditions, okay, or beyond sonic conditions, beyond sonic conditions. So first you'll have the converging part where the fluid keeps accelerating and it reaches Mach number equal to 1. So after Mach number is equal to 1, if you want to further accelerate the flow, you should have a diverging cross section. That's why the rocket nozzles are something like this, okay. So initially till this part you have the acceleration and further acceleration because you want exhaust velocity to be as high as possible because of Newton's third law, and this equation is really an important equation, okay. And for subsonic flows in converging nozzles, you'll see velocity will increase and Mach number will increase, and rest, this pressure, density, temperature, all these things decrease, okay. And anyway, all this inside is not known in a rocket okay. Normally you will see only this part outside, okay, but in reality inside this is what you get, okay. So these are the things. Again, we can derive all this stuff using the simple equations, okay. Yeah, here area velocity relations, converging nozzles I have taught maybe. So this is what, okay, you take some area, apply again some momentum, energy, mass balance equations and all these things, okay. But crack nahi kiya to पूरा 8 months का total loss हो जाएगा. नहीं, see, never think like that, okay. Just keep focusing and attempt the things. Yes. So see, this is the continuity equation I have started with, and somebody that day asked me how this, initially I wrote this from this, then I still remember somebody asked how did you write from this to this directly, then I have explained how did I write that, okay. I remember these things. It's because it's all for GATE 2025 and the exam is so close. So after doing a bit of understanding, you will get this relation, okay. So depending on the relation, then you can figure out a lot of things like converging nozzles, diverging nozzles, all the things, and why pressure decays, all these examples, explanations are given, and finally you figure out this result, whatever I have written here, okay. So velocity increases, Mach number increases, and things decreases. If you have a supersonic nozzle, like if you have supersonic flow in a converging nozzle, then ultimately this velocity and Mach decreases, P, rho, T, they increase, okay. And similarly, if you have okay, so similarly if you have converging nozzles, okay, converging nozzles and all, then it's okay, no issues. So in converging nozzles you will have the flow patterns, and you will see the Mach at Mach number is equal to 1 where is the choking conditions. Clear? And I mucked up whole things, but you cleared the concepts, no? Okay, so you can see this, and obviously once you know the mathematical analogies, you can just do a lot of stuff, okay, converging, diverging nozzles and all. So somebody asked me this, okay, I myself have solved this GATE 2023 question, compressible flows. It's a simple question after knowing all these points. Again, stagnation, so critical conditions, we have done a lot of stuff, okay. So converging nozzles, so in converging nozzles, depending on the back pressure, how things keep changing, okay, so how flow happens. Anyway, these things again, if you go into deep, they keep extending, okay. So I'll do one thing, maybe I'll ask permission, and if people are okay, I'll upload these notes in the Telegram channel for the compressible flows, okay. Because again, right now just giving so many formulas will not look like a very convincing way. Just maybe I can show you some colorful diagrams, and I can teach you that, I can show you that I taught this, I taught that and all, but at the end it won't be very fruitful for you, okay. The shocks is in the last lecture, of course, whatever I have taught you, per gate. So you'll see after teaching converging nozzles, then I have started converging diverging nozzles. So this is why Mach number is equal to 1, this area ratio function of Mach number, all these things, and converging diverging nozzles. So at this point you'll see there's a shock, and so once you identify the shock, it's important for you to analyze shocks. Okay, so this is shock analysis, normal shock analysis, of course. Again, mass conservation. Okay, then momentum balance. This is also RTT again. Okay, across the shock you take the control volume and apply some momentum balance, energy balance, then entropy balance, which is of course shock is highly irreversible. Then all these expressions which you see we have done, P1 by P2. Normally these things you might have seen at the end, towards the end, where if you have a shock, then upstream and downstream the shock, how things change up. We have done mathematical explanations to all these things. And this is downstream the shock, Mach number. So just in front of the shock, if you know the Mach number and if you know the fluid, then after the shock what's going to be the Mach number. Okay, and so across the normal shock, after doing so many analysis, we figured out some numbers. And so these are the Rayleigh and Fano lines which I have taught. Yeah, Mach cone, of course. And then after we have solved the questions. Okay, but anyway, I'll try to do one thing. I'll ask permission, and if people are okay, then I'll post these notes. Okay, clear? That's the compressible flow part, which is more than enough for gate if people wanted to know. Will you teach in ESC batches? To be frank, I don't, because as of now we have only ESC batches in English, in Hindi. So, and majority because of my schedules, and I teach these subjects in 2 cycles every year, so schedule gets logged in English batches itself. Hello. Anyway, so V, Mach number, P, O, T, all these things changes. Okay, so I'll upload the notes for that, because again mugging up so many formulas doesn't help. Okay, so just solve this question. An aircraft flies at Mach 2.3 at about 11 kilometers standard altitude. The temperature at the stagnation point is dash. So let's see. So aircraft is flying at Mach number 2.3 and altitude is 11 kilometers standard altitude. So temperature at the stagnation point is dash Kelvin. So you know temperature at the stagnation point is T into 1 plus gamma minus 1 by 2 Mach square. Correct? Is this the expression I have given you just some minutes back? Yeah, correct. Mach square by 2. So here you know everything, but you don't know what is this T. What is the temperature at height of 11 kilometers? Okay, so if you remember, maybe in Maha Abhyas I did not teach you, but normally some of you have seen T naught or T at sea level minus alpha Z. Okay, so this alpha is called lapse rate. Okay, so alpha is called the lapse rate, and so T at 11 kilometers is equal to, at sea level this is normal temperature is 15 degrees Celsius, so 288.15 minus alpha, this lapse rate is 6.5 Kelvin per kilometer. So for every 1 kilometer difference, for every 1 kilometer you go up, you will see a temperature difference of 6.5 Kelvin. Anyway, degrees Celsius, ours Kelvin, this is just a difference. So 6.5 into 11. Okay, so this gives you some T in Kelvin. So 288.15 minus 6 into 11, so 66, no, obviously, to 222.15. So this is 222.15 Kelvin. Okay, so which is like 66 minus 30, something like that. Okay, sorry, minus 50 almost. So you know T naught is equal to 222.15 into, obviously you have air, so gamma is 1.4, so 0.2 times of Mach square. So it's flying at a Mach 2.3. Okay, so 0.2 into 2.3 square, 1.058 plus 1 into 222.15. Okay, so if you subtract 273 from this, anyway, just for the idea I'm doing 457.18 Kelvin. Okay, so if you have 457.18 Kelvin, this is almost equal to 184 0.18 degrees Celsius. Now, did you understand? If an aircraft is flying at that altitude, 529.6 Kelvin, where? This one. Whatever. This is correct. Okay, Pawan. This is correct. And normally you'll see, which tells you that if a plane is flying at a altitude of 11 kilometers at a height of 2.3, where the atmospheric temperature is minus 50 almost, the temperature at the tip of the plane is 180 Kelvin. Sorry, 180 degrees Celsius. Understand how hot it is when air can, how hot damage this air can do. Okay. So anyway, I just wanted to give you so many other questions as well, but yeah, this is again isentropic flow in a channel of varying area. So let's solve this question. Solution. So consider isentropic flow in a channel of varying area from section 1 to section 2. Okay. So from section 1 to section 2, so let's say this is section 1 and you have section 2, of course. Okay. So area is changing. So if area is changing, Mach number at section 1 is 2. So Mach number at section 1 is 2. Okay. And what about the desired velocity ratio? V2 by V1 is 1.2. So V2 by V1 you need is 1.2, which means you want to generate V2 which is greater than V1. Okay. And initially this is supersonic condition. Supersonic condition. Okay. Is it due to drag? Yeah, viscous drag, of course. Okay, in reality. But this concept of stagnation will also have the dynamic temperature impact, and that will increase. Okay. So supersonic conditions. So choose the correct statement. So imagine, I'll ask you one thing, observe carefully. Here you have the supersonic entry, and in a supersonic case you want to further increase the velocity of the flow, correct? So you already have the supersonic inlet and you want to increase the flow, then this cross section should be converging or diverging? Tell me. This cross section should be converging or diverging? I've just told you, if subsonic, then for the fluid to accelerate you should have a converging nozzle. That's why in all your fluid mechanics problems normally till this point, whatever you have seen, we'll see that the velocity increases in a converging nozzle. But now it's supersonic, so for the fluid to further accelerate you need a diverging nozzle. Okay. So for this implies nozzle should diverge or area should be diverging. Area should be diverging actually. Okay. So the channel is a diverging channel. See. Then Mach number at section 2 in the range of 2.7 to 3.1, Mach number at section 2 in the range of 3.6 to 3.9. So in this supersonic inlet you have the further increase. So what is the Mach number at location 2, of course. Okay. So you see this can be written as V2 upon A2, and this V2 can be written as 1.2 times V1. Okay. And it's a diverging cross section. So at the corresponding velocity, what is the acoustic velocity? Okay. So how we can manipulate A2? So we see at this point and at this point the stagnation enthalpy should be same. Okay. Because if you look at Q minus W equal to delta K plus delta P plus delta H, all this stuff, then stagnation enthalpy should remain same. So stagnation temperatures should remain same actually here. Okay. So this can be written as, so stagnation enthalpy should be same. So stagnation enthalpy can be written as, so let's say at some point, at this point if the temperature is T1, then correspondingly T1 times 1 plus gamma minus 1 by 2 Mach 1 square is equal to, at this point if temperature is T2, so T2 into 1 plus gamma minus 1 by 2 Mach number square. Okay. But how do you connect T1 and T2? So this is given. So if that's given to you, then T2, anyway, no need to do this then. So how do you get T2 actually? This is known, Mach number at 1 is known, so this is 4. Gamma is known, substance is air, correct? So gamma is 1.4, correct? Because you see, consider the isentropic flow in a channel of duct weighing, okay, of air, you can say of air. Then V2 by V1 is this, so Mach number. So normally if there is a shock we can do very straightforward, but there is no shock here, so this T1 and T2, how we can connect to V1 and V2 is what I am thinking. Okay, so just from the steady flow energy equation, V1 square by 2, V1 square by 2 plus Cp into T1 is equal to V2 square by 2 plus Cp into T2. Okay, that's what you would get. So this tells you T Cp or T2 minus T1 is equal to V1 square minus V2 square upon 2 Cp. So I think you can connect some velocities actually here, okay, from the steady flow energy equation. So let's see, V1 square minus V2 square by 2 Cp, and it's an isentropic flow of air, correct? They have mentioned this word, isentropic flow. So area is diverging, okay, so T2 minus T1, which is V1 square minus V2 square by 2 Cp. So T2 upon T1 is what you need actually, okay. So T2 minus T1, okay. So how do we do this? Stagnation enthalpy has to be same, and of course this is also the same equation actually, but V1 and V2 are known to you. So if you take T1 common, I am trying to think, yeah, T1 is missing I think, no? But without T1 I think you can still solve this question, because in a supersonic flow if you have the velocities ratio you can get the Mach numbers ratio also. So let's see, Ma2 by Ma1, if you write V2 by V1 into A1 by A2, which is equal to V2 by V1 into square root of T1 by T2, because gamma RT 1, and this ratio is known to you, this is known, this is known, so this you should get T1 by T2. Of course even the case is same here, okay. So if you get T1 by T2 it can be done, but how come you do this? I think some data is missing, no? Maybe, correct? So some input I think is not there, or are we not able to think the input, because we are having two unknowns in either cases. So 1 A1 V1, so 2 A2 V2, but again you will have two unknowns. Okay, I think T1 is missing maybe here, so T1 should be known. Okay, so once T1 is known, then obviously you can calculate T2 and do these calculations. Okay, so T1 should be known. Hello. If T1 is given, then you can solve this, of course. Okay, fine. So let's go to one last topic, which is hydraulic machines. This is the last part actually, okay. So for any turbo machine, actually, so if you see the head delivered, which is per unit weight, is Vw at inlet, velocity of the blade at inlet, minus Vw at outlet, U at outlet by G. This is what you would get, okay. And in this case, if you have this Vw in, U in, minus Vw out, U out, divided by G actually, okay. So then using velocity triangles, okay. So at any point the velocity triangles can be written like this. So if you have the velocity V and you have the velocity of the blade U, then clearly this would be the relative velocity. Okay, and this absolute velocity which is here can be resolved into two parts. One is the tangential component. Normally if this is the tangential direction, sorry, this is the radial direction because u is the tangential component, so radial. And if you have tangential, then this is VW and this is VF, which is the flow component or the radial component actually. Okay, so this is VW and VF. So this angle is the nozzle inlet angle alpha, and this is the relative angle which is beta, or generally called as theta, phi, all these things. Okay, or alpha 1 and beta 1. Similarly at the outlet beta 2 and alpha 2. So this is the actual velocity, but because of the blade velocity here u, so we have some relative velocity which takes place. Okay, and from velocity triangles this h can be written as v1 square minus v2 square by 2g plus v or u1 square minus u2 square by 2g plus vr2 square minus vr1 square upon 2g. So this is what you would get. Okay, so plus vr2 square minus vr1 square by 2g, and you can see this part whatever you have, this is due to the difference in pressure head P1 minus P2 by rho g. From Bernoulli's equation you can get this, the head which is delivered. Normally in this full analysis we don't take any viscous effects, so that's how we have P1 minus P2 by rho g. So normally in case of axial flow machines this happens in the stator and this happens in the rotor of course. Okay, in reaction machines this will contribute. So normally we define some quantity which is called as degree of reaction. Reaction which is, of course, when you go for steam and gas turbines in thermodynamics we define that as delta H in the stator by total delta H in the full stage. Okay, and here you will see this is 1 by 2g u1 square minus u2 square plus vr2 square minus vr1 square by h delivered, which is nothing but 1 by 2g v1 square minus v2 square plus u1 square minus u2 square plus vr2 square minus vr1 square. Okay, so this is what you have the degree of reaction. Okay, and normally in cases we'll see where if there is no blade frictions and all, this vr1 vr2 are almost the same, and this u1 and u2 in few cases if it's same then the numerator is 0 and this r becomes 0 actually. Okay, so that's called impulse machines. Okay, so and for reaction machines 0 less than r less than 1. Okay, so there are things like where we talk about the degree of reaction and all, and you'll see if you do modeling of the turbines, for example modeling, then the power output of any turbine depends on certain variables. Okay, and these variables are discharge flowing, speed, diameter of the impeller, GH, rho, mu, bulk modulus. Okay, so these things. So in general we have some function of P, Q, N, D, GH, rho, mu, E is equal to 0. Okay, then there are 8 variables, and of course these 8 variables involve only 3 fundamental dimensions, so you have total 5 pi terms. Okay, so what are those 5 pi terms? Let's see. If you do dimensional analysis, okay, so if you do the dimensional analysis then you will end up with pi terms as some function of P by rho n cube d power 5, Q upon n d cube, GH by n square d square, mu by rho n d square, and bulk modulus of rho n square d square. So this term is equal to 0. So this 8 8-dimensional quantities will reduce to 5-dimensionless groups. Okay, and this is called the power coefficient. Power coefficient, and this is called flow coefficient, and this is the head coefficient. And if you observe correctly, this is the Reynolds number and this is Mach numbers, of course square of the Mach number actually, and this is Reynolds number. Okay, and if you try to model the turbines, then obviously like how you do in the dimensional analysis, you will model using this dimensionless combinations. Okay, and this is when you are modeling the turbines. But if you actually try to talk about the same turbine but at different operating conditions, or same pump at different operating conditions, we go for unit quantities. Okay, so the unit quantities tells you unit quantities. These should be used for same machine at different operating conditions. At different operating conditions. Okay, so like if you see, normally if you do some analysis, you will get these options. By root H1 should be same as N2 by root H2. This Q1 by root H1 will be equal to Q2 by root H2, and power by H power 3 by 2 is equal to P2 by H power 3 by 2. Okay, so you should use these quantities if you are changing the performance parameters of the same machine. But if you are using the performance parameters of, if you are trying to model, okay, then you should make sure these things are equal actually. Okay, so let's solve one question again. So to solve this question, let's solve this solution. A turbine operating under a head of 32 meters, so H1 is 32 meters, develops a power of 9000 kilowatts. Okay, so 9000 kilowatts at a speed of 100 rpm. Power developed by the turbine, so the same turbine is being used. So what is P2 when head is reduced to 16 meters? Okay, so since it's the same turbine, we'll use this unit quantities. Therefore P2 is equal to P1 into H2 by H1 whole power 3 by 2. Okay, so P2 is equal to 9000 kilowatts into H2 by H1 power 3 by 2. So this is 2. So this value would be in some kilowatts. 9000 by 2 power 1.5. Okay, so this gives you 3181.98 or 3182 kilowatts. Okay, so that's the power which is given if the machine operates at a head of 16 kilowatts. 25455.944. If head is decreased, how power can increase? Okay, so this is the correct answer. 3182 kilowatts is the answer. Okay, so this is how we do the things. Now the only thing is, like, whatever the turbines you have, whatever the equations you got, okay, you will keep applying them for various machines. Maybe I'll just show you because yesterday someone has asked me. So I have recently taught you fluid mechanics, no, sometime back. Yeah. Yeah, these are the two lectures in which I taught hydraulic machines. So, okay, so if you see, so these are the complex functions, of course, okay, in the potential flows. But anyway, so here it started. So turbo machines, yeah, I think some homework I have given that day. So turbo machines, RTT. So from RTT showing the Euler's equation and all, you will see finally we'll get this equation. Okay, so H is theta or VW, tangential components we'll use. Okay, so some, if you have the blading, then how the velocity triangles are formed. Okay, then how to analyze those velocity triangles, we done these things. Conversion from this to this formula which I have given you now, and degree of reaction, blade coefficients, everything. So terminologies like hydraulic efficiencies, all this stuff, okay, values, nominal values, impulse and reaction principles. So this is the Pelton wheel, okay, which we have drawn that day. So the Pelton wheel normally has a rotor and the buckets on top of it, okay. So you can see a Pelton wheel here. So when the fluid comes and hit, okay, then this wheel will rotate, okay, and when this wheel rotates, we have done some analysis again, so which gives you the power. This is the blading and all. So we will see that for the maximum hydraulic efficiency, means for the best operating conditions, the bucket speed should be half of the jet speed, okay. So we do all these things. So in Pelton wheel, normally if you see in Pelton wheel, the U by V, U is the bucket speed, the tangential velocity of the bucket, and V is the jet velocity. So that gives you half. So the principles are same, but we keep applying them for different machines, okay, that's all. And again in the second lecture, you'll see we go for the Francis turbine and the Kaplan turbines, okay. Some homework I have given, and so Francis and Kaplan turbines is what we'll see. So Francis turbine, the general Francis turbine, which you see the fluid enters spiral casing, everything, and just a bit of analysis, that's all. The formulas remain same, the draft tube, all this stuff. Then axial flow machine, okay. So you have the Kaplan turbine like this, axial flow machine, and the velocity triangles of the axial flow machines, everything. See, you can apply your velocity triangles concept to any machine, okay, depending upon the geometry, just the triangle shape changes. Apart from that, nothing changes, okay. Whatever the things I teach in the first half an hour, the things remain the same, okay. So anyway, you in PYQ's class, okay, so combined velocity triangles, whatever. So I know, so in today, head formulas are once again for machines. The head formula is given by the tangential velocity into the tangential component of the fluid multiplied with the tangential component of the tangential velocity of the blade at that inlet minus outlet divided by G, okay. So basically I understand that in today's class I did not solve questions like from few places like turbulent flows, okay, then fluid and its properties. So the places where the weightage is very low. So whenever is draft tube and NPSH important for 2025, they are not in syllabus of GATE, okay, don't worry. So in GATE syllabus they are not there. Then so I haven't touched concepts where it involves like plates and all, because in yesterday's class in Maha Abhyas I have solved first three chapters questions very effectively. So that's why I did not put many questions today. And turbulent flows being a very small chapter, I did not put any questions. So when I solve PYQs on 11th of January, so you'll see that on 11th of January, tomorrow, we have not tomorrow, sorry, Saturday at 2 p.m. in the afternoon on English channel, we have PYQ solving. So in PYQs, I'll put more questions from turbulent flows, so at least some 2-3 questions from 1-2 questions from turbulent flows, or what are the other chapters which we did not touch, like first chapter, fluid and its properties. So these are the 2 chapters mostly. So from these 2 chapters and also this turbo machines maybe, okay. So we'll put some 2-3 questions from here as well. So we'll make sure that all the important and also some nice PYQs which you don't have, we'll cover those things, okay. So for maths 2025, as of now, solve PYQs. Like recently I have posted a video on English channel, like how to get 13 out of 13 in maths, at least not 13 out of 13 in reality, but at least more than 10, 11 till that point you can easily get if you follow those techniques, okay. On English Wallah channel I have posted the video how to get maximum marks in maths. So just go through that video. It's a short video, 7 minutes video I have made, because I don't want to consume your time at this point. So I made a short video of 7 to 8 minutes. So just follow that, okay. Everything I've taught there, okay. Important topics for maths, all these things. So normally if you see again, it's like a full syllabus. If I start telling you, it'll be like full syllabus, but generally recently in mechanical you'll see who is this Ananya Gupta? Adarsh Kumar Verma, okay. Hope he sees the messages. Laminar pipe flow, head loss varies linearly with velocity. Why this statement is wrong? It varies with square of the velocity, no? If you remember, HL FLV square by 2GD. So HL is proportional to V square. Okay. Irreversibility is T naught into del universe or generation. Delta S of universe or delta S of generation, both are same, na? Because universe cannot have any entropy with heat interaction. It's okay, let's not have personal discussions here because I can't help it out. It's an individual decision. So anyway, so coming to the maths. Okay, so in the maths, okay, so in the maths, basically you work out on the probability and statistics, this distributions part. Okay, normal distribution. Okay, normal distribution, and you can have normal distributions basically, and random variables, general calculations on random variables. See, for maths, just try to follow the test series. Okay, because I'm trying to put those questions where which are very frequent in nature. Okay, that's better. I'm just lacking because of getting less numbers in the test series and just blank while giving the test. When you open the test, or after opening the question paper, first sit relaxed for 2 minutes, get yourself calm, and then start the test. Okay, some 2-3 minutes you spend on calming down first. I understand to few people it happens, anxiety will keep coming up, but no need. Why buoyancy force of ball is 0? Ball volume is very small. It's not 0, it's neglected compared to the other terms. Okay, even if you consider the ball buoyancy and do the calculation, you'll see very less difference, less than maybe some 1% or 0.5%. Okay, does UPSC mechanical have fluid mechanics subject? Yeah, of course, why not? UPSC mechanical has fluid mechanics. Okay, like almost some, last time it came some 30 marks in mains, and in prelims it's like almost out of 150. There are like some out of 150 questions, out of 300 marks actually, out of 150 questions and 300 marks, you got around some 25 to 25 marks. Okay, how to join ISO? They'll keep exam, just write it. Bhupati, H is equal to U plus PV, DH is equal to DU plus PdV plus VdP. At constant pressure, H is equal to DH is equal to DU plus PdV. If we apply DH is equal to CPdt, DU equal to CVdt, PVdV equal to NRdt, we get Cp minus Cv equal to INR. My doubt is, we said constant pressure, then why we applied DU? Because for ideal gas, irrespective of the process, DU is always CVdt. Okay, for ideal gas, and of course that's not the general way to derive the ideal gas equation. There is some different way, but anyway, if you see, we'll use something called Mayer's equation. From Mayer's equation we get the ideal gas equation. But anyway, in your case, whatever the equations you have written, DU is CVdt for ideal gas for any process. Okay, so as long as you're dealing with ideal gas, DU is CVdt. Okay, which can be shown, all mathematical I have done in the thermodynamic relations. But we all have this equation, no? DH is equal to, or DH is equal to CPdt plus V minus T dou V by dou T at constant pressure dP. Okay, so these things we have done actually. Okay, so from there you will see. Okay, can we have CFD series? Not now, maybe. Okay, maybe after some, at least let the gate exam, XC with BRC, everything get done, then we'll see. Okay, so thank you, Adarsh, take care. Yeah, fine. So thank you all. We'll meet in the PYQ series on Saturday at 2 p.m. Okay, and tomorrow we have the Maha revision of manufacturing process first part, so do attend without missing. Okay, because manufacturing is also a very big subject, has some good weightage, so just attend tomorrow. Till then, thank you. We'll meet on Saturday again at 2 p.m. Yeah, okay, bye.